Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Silence. In the beginning, there is nothing but the deep dark of space. Cold, still, primordial. Then motion, a subtle stirring in the void. Out beyond the known planets, a distant glimmer emerges from darkness. An icy fragment, left over from the solar system's birth, has been jostled from its slumber. A comet is coming to life. It is ancient and newborn all at once. A time traveler from the dawn of creation, a survivor of billions of years, a frozen relic of our origin story. Each appearance of such a wanderer is a return and a reminder, as if the cosmos itself has memories to share. The comet begins its long fall toward the inner sun, carrying with it the secrets of a beginning. It was there at our solar system's first breath, and now, after ages of quiet, it moves again. Far from the sun, at the very edge of our solar system, lies the comet's birthplace, a vast unseen halo of icy bodies encircling the sun like a ghostly sphere. Here in the Oort cloud, trillions of frozen fragments drift in a great cosmic shell, so distant that the sun is merely another star in the sky. This is a realm of deep freeze, where comets spend most of their lives in exile. Temperatures hover just a few degrees above absolute zero, cold enough to preserve primitive ices for eons. In this dark sanctuary, time moves slowly. The comets are effectively in suspended animation, pristine and unchanged since the solar system was young. They carry water, methane, ammonia, carbon compounds, the ingredients of planets and life, locked in an icy matrix, safe from the sun's heat. Each one is a fragment of our origin, a piece of the protoplanetary disk cast outwards long ago and kept on ice. For millions upon millions of years, these cosmic snowballs circle invisibly at the solar system's frontier, like embers frozen in ash, waiting for a chance to glow again. What can trigger such a slumbering comet to awaken? Often, it is the gentle but inexorable tug of gravity, a disturbance from outside or within that nudges the comet onto a new path. Perhaps a distant star passes near the sun, and its gravity ever so slightly perturbs the orbits in the Oort cloud. The Milky Way itself exerts a tidal force, a gravitational rhythm that can slowly shake comets loose from their moorings. It has been said that up to 9 out of 10 long-period comets that visit us may owe their journeys to the subtle tide of our galaxy. Over immense spans of time, these influences add up. A comet that once traced a quiet, circular path, a light year from the sun, finds its course changed ever so slightly, enough that it begins to drift inward. Sometimes the trigger is sudden. A passing star like Schultz's star brushes through the outer cloud, as happened some 70,000 years ago, dislodging comets in its wake. Or, in the distant future, another star will plow through the Oort cloud in a few million years, sending a rain of comets sunward. Even the giant planets can play a role for comets that dwell in closer reservoirs. A gravitational nudge from Jupiter or Saturn can redirect a comet from the Kuiper belt or inner Oort disk onto a new, plunging trajectory. And so, by fate or chance, one frozen body is knocked off course. It begins a long fall, pulled inward by the sun's gravity after an eternity in the cold. The silence of the outer dark is broken. The comet has embarked on a voyage that will transform it utterly. At first, as the comet journeys through the outer reaches, nothing visible happens. It is still too far from the sun, an unseen traveler in the interplanetary night. But slowly, inexorably, the solar warmth grows. The great journey may take millions of years from the comet's perspective, arcing slowly from the black outskirts toward the faint glow of the inner sun. As it crosses the orbit of Neptune and Uranus, the comet remains essentially a dark, icy nucleus, perhaps a few kilometers across, still cloaked in vacuum. But already, the sun's influence is mounting. The most volatile substances in the comet, gases like carbon monoxide and carbon dioxide, which turn to vapor at very low temperatures, begin to sublimate off the surface while the comet is still far from the sun. Even out near Jupiter's orbit or beyond, a large comet can wake up in subtle ways. Comet Hale, BOP, one of the brightest comets in modern times, was detected venting jets of carbon monoxide when it was further from the sun than Saturn, a ghostly breath in the frigid dark. Such outgassing is almost imperceptible to the naked eye, a faint haze around the nucleus, but it heralds the beginning of a comet's transformation. As the comet draws closer to the inner solar system, the sun's rays grow stronger and the pace of change quickens. Crossing the orbit of Jupiter and heading toward Mars' domain, the comet warms enough for water ice, its primary ingredient, to sublimate. What was once a solid, frozen mass now begins to unleash vapor. Jets of gas burst from beneath the surface, where sunlight heats pockets of ice, carrying with them clouds of dust particles that had been embedded in the ice. A tenuous atmosphere forms around the comet's nucleus. We call this the coma, a glowing halo of gas and dust that envelops the tiny nucleus like a luminous shroud. At first, the coma is thin and small, but as the comet approaches the inner solar system, the coma can expand to enormous size, often tens of thousands of kilometers across, dwarfing the nucleus that spawned it. Around some comets, a vast, invisible cloud of hydrogen gas also blooms, a halo that can be millions of kilometers wide. The traveler that was once a dark, icy rock has become something entirely different, a bright, active comet, announcing itself with a growing cocoon of vapor and dust. Now the sun's influence truly takes hold, sculpting the material blowing off the comet into dramatic structures that sweep across space. Solar radiation, the steady stream of light and energy from the sun, presses upon the dust in the coma, and the smallest particles begin to be pushed outward, away from the sun. At the same time, the sun's wind, a flow of charged particles streaming out at hundreds of kilometers per second, catches the gases of the coma and drags them into a long plume. The result is magical. One coma, but two distinct tails unfurling behind the racing comet. A dust tail blossoms, formed of fine grains of comet dust, reflecting sunlight. It often appears broad and gently curved, a pale fan that can stretch millions of kilometers and often has a yellow-white hue to our eyes. This dust tail traces the comet's trajectory like a painter's stroke across the stars, curving because the dust grains, having mass, lag behind the comet's head and continue along the comet's orbit even as sunlight slowly shoves them aside. The other, more ethereal filament is the ion tail, made of gases, carbon monoxide, carbon dioxide, nitrogen, water vapor, that have been ionized by ultraviolet sunlight. These ions glow faintly, often in a blue or bluish-green hue, and being charged, they respond to the sun's magnetic field carried by the solar wind. The ion tail shoots straight away from the sun, a narrow, sword-like beam that can extend for tens of millions of kilometers, directly opposite the sun, regardless of which way the comet itself is moving. If you could hover in space, you would see the ion tail always pointing away from our star, sometimes leading the comet when it departs the sun, sometimes trailing it as it approaches, but always oriented by that invisible solar breeze. The comet now is fully awake, a cosmic apparition with a glowing head and trailing tails, hurtling faster and faster as it draws near the sun's embrace. Its anatomy is laid bare in this moment of brilliance. At its core lies the nucleus, the heart of the comet, a small, dark body, typically only a few kilometers across, made of ice, rock, and complex molecules. A comet's nucleus is often an irregular, potato-shaped lump, far smaller than a city, yet it holds within it the potential to create spectacles spanning the sky. One might expect such an ice-rich body to shine brightly, but comet nuclei are surprisingly dark, blacker than coal, coated with dust and carbon, rich material. Indeed, a typical nucleus reflects only a few % of the sunlight that hits it. Scientists have found the surfaces of comet nuclei to be among the darkest materials in the solar system, likely because as ices sublimate away, they leave behind a crust of organic, rich dust. This dusty blanket absorbs sunlight, causing pockets of subsurface ice to heat and erupt in jets, the very process feeding the coma and tails. Surrounding the nucleus is the coma, a diffuse cloud of gas and dust grains that glows as sunlight scatters through it. To an observer on Earth, the coma often appears as a fuzzy, star-like core at the head of the comet. In fact, the word comet comes from ancient Greek kometes, meaning long-haired star, inspired by that misty head and trailing hair, like tail. From within the coma extend the two great tails, the broad, curving dust tail, glimmering with reflected sunlight, and the straight, often bluish ion tail, shining by fluorescing gases. The ion tail, being made of charged particles, is subject to magnetic whims. Ripples in the solar wind can cause it to kink or even detach. At times, astronomers have watched a comet's ion tail get ripped away by a particularly strong solar gust, only for a new tail to grow in its place as the comet continues to shed gas. These disconnection events are vivid reminders that a comet's graceful form is shaped by an ongoing interaction with our tempestuous sun. Dust tail and ion tail together turn the once invisible nucleus into a spectacle that can span half the sky. A comet at peak activity is like a giant paintbrush streaking away from the sun, its nucleus the handle, its coma the brush head, its twin tails the strokes of color on the canvas of night. What gives a comet's coma and tails their glow is not just sunlight, but the very substance of the comet itself, a rich chemistry that links these wandering ice balls to the origin of life. As the ices in the nucleus vaporize, they release not only water, but a menagerie of molecules that had been frozen inside. In that diffuse coma, scientists have detected some of the fundamental chemical building blocks that predate biology. There is water, H2O, the same simple molecule that fills Earth's oceans. There is carbon dioxide and carbon monoxide, the same gases that can shroud a planet's sky. Ammonia, methane, molecular nitrogen, simple compounds that carry the essential elements of life, stream away from the warming nucleus. Traces of more complex and sometimes toxic gases appear too. Hydrogen cyanide and cyanogen are commonly detected, which in ages past led fearful observers to imagine comets poisoning the Earth. Organic molecules form a substantial part of the outpouring. Formaldehyde, methanol, and other carbon-bearing molecules are common in cometary vapor. Perhaps most intriguingly, comets have been found to contain amino acids, the building blocks of proteins. In 2006, scientists studying samples from Comet Wild 2 discovered glycine, the simplest amino acid, embedded in the comet's dust. It was the first time an amino acid was confirmed in a comet, a discovery suggesting that these objects carry some of life's raw ingredients and can disperse them through space. Comet 67P, Churyumov, Gerasimenko, visited by the Rosetta spacecraft, provided a similar revelation. Rosetta's lander sniffed a suite of organic compounds on 67P's surface, including amino acids and phosphorus, key elements for DNA and cell membranes. It is a profound thought that a comet's brilliant tail, so beautiful to the eye, is in fact laden with the stuff of life's chemistry. Each shimmering trail is like the ghost of an ancient chemistry experiment, dispersing water and carbon across the heavens. This realization has led scientists to hypothesize that comets may have played a pivotal role in Earth's own story. Our planet formed dry and hot, likely unable to retain water in its early years due to intense heat. So where did Earth's vast oceans come from? One idea is that comets, rich in water ice, rained down on the early Earth, delivering water that pooled into seas. Along with water, they could have brought organic molecules, giving a boost to the prebiotic soup from which life emerged. Indeed, comets are time capsules from the birth of the solar system, preserving the kinds of materials that would have been present when Earth was young. Perhaps it was cometary impacts that seeded our infant planet with the volatiles and carbon compounds it needed to become a living world. This is the impact hypothesis for life's origins, that the violent delivery of cometary material was also a gift. Water for oceans, carbon for organic chemistry, maybe even complex organics that jump, started life's emergence. As poetic as it sounds, it finds some support in evidence. Certain comets contain water with isotopic ratios similar to Earth's oceans, implying a common source. A notable example was Comet 103P Hartley 2, whose water was found to closely match Earth's in composition, hinting that at least some comets could have contributed to our seas. However, not all comets fit the bill. Rosetta's measurements at Comet 67P showed its water was significantly heavier, suggesting that particular comet did not stock Earth's reservoirs. The debate continues, with current thinking pointing to a combination of sources delivering Earth's water. But beyond water, the notion that comets fertilized the early Earth with organic molecules remains compelling. Experiments show that amino acids can indeed form in comet, like ices under cosmic radiation, and comets have clearly shown they carry such molecules. Comets, in this light, are both harbingers and gardeners, capable of sowing life's ingredients, even as they portend destruction. Destruction is the other edge of that cosmic sword. The same impact deliveries that might have nurtured life can also wreak havoc. Comets have slammed into planets many times. We have a front row view of such a catastrophe from July 1994, when Comet Shoemaker, Levy 9, collided with Jupiter. This comet had been torn into fragments by Jupiter's gravity, and one by one, its pieces smashed into the gas giant, each impact releasing energy equivalent to millions of nuclear bombs. Earth-based telescopes watched in awe as fireballs erupted on Jupiter, and dark scars, larger than Earth in diameter, marred Jupiter's cloud tops. Those bruises on Jupiter were an eerie reminder. If such a comet were to strike Earth, the consequences would be apocalyptic. Indeed, some scientists speculate that a comet impact may have caused upheavals on our planet in the past. The mass extinction that ended the dinosaurs 66 million years ago is usually attributed to an asteroid, but it is conceivable a long-period comet could also cause such an event. In more recent geological history, there are hints, albeit controversial, that a sudden climate downturn 13,000 years ago might have been triggered by fragments of a disintegrating comet striking or air bursting over Earth. Whether or not comets can be definitively tied to past extinctions, they surely have the power to cause them. Even a small comet, only a kilometer or two across, hitting Earth would release more energy than all the world's nuclear weapons combined. The notion is terrifying precisely because comets often arrive with little warning. Unlike the asteroids we are mapping and tracking, a long-period comet from the Oort cloud can appear in our skies with only a few months or a few years' notice. It hurtles in at enormous speed, perhaps 50 or 70 kilometers per second relative to Earth, much faster than a typical near-Earth asteroid. That high velocity means an impact carries tremendous kinetic energy, and as comets approach the Sun, they can also unpredictably brighten or fragment, complicating efforts to gauge their size and trajectory. All this makes them challenging targets for any hypothetical planetary defense. A sneaky, long-period comet might be detected only a short time before a potential impact, leaving us scant time to prepare. It's a cosmic game of chance that humanity must take seriously. So while we marvel at comets, astronomers also keep a wary eye on them. Surveys scan the sky for new comets, and space agencies contemplate how we might deflect or evacuate if one were ever found on a collision course. The menace is low, probability. Impacts by large, long, period comets are extremely rare on human timescales, but the potential consequence is high. Comets, then, embody the duality of nature, creators and destroyers, preservers of life's ingredients, yet capable of mass extinction. They remind us that our planet's story is intertwined with the capricious theater of space. One world's gentle rain of water may be another world's cataclysm. As we look up at a comet's beauty, we cannot forget the danger in its halo. And yet, in these icy visitors, we also see archives of the earliest history of our solar system. Each comet is a celestial archivist, preserving in its frigid nucleus a record of conditions from over 4.5 billion years ago. Locked away in that dark, porous ice are tiny grains of dust, older than Earth, some perhaps older than the Sun, solar grains from ancient stars. The composition of comets, the ratios of isotopes in their water, the mix of organic molecules, the presence of noble gases, all carry information about the environment and processes that prevailed when planets were forming. When we study a comet, we are in a sense reading a memoir of the solar system's youth. Comets have been called time capsules by scientists, and rightly so. Untouched by geologic activity or intense solar heat, a comet's nucleus can preserve volatile compounds that would long ago have disappeared from planets. For instance, the detection of molecular oxygen streaming from comet 67P was a great surprise. O2 is so reactive that it's rarely found in space except as a byproduct of life. Yet Rosetta found abundant O2 in 67P's coma. The discovery suggested that the oxygen was primordial, trapped in the comet since the solar system formed, and only now being released. Thus, comets can carry unexpected relics of the chemistry of the protoplanetary nebula. Similarly, the mix of minerals in comet dust has astonished scientists. Samples from Comet Wild 2 contained not just the expected ices and interstellar dust, but also minerals that form at extremely high temperatures, like olivine and CAIs, materials typical of the inner solar system near the early Sun. Their presence in a comet that formed far out beyond Neptune implies a grand radial mixing occurred in the early disk. The infant Sun's ferocious winds or jets must have blown these fire, forged grains outward, or perhaps turbulence stirred the pot, embedding a bit of sun, fire in bodies born in the icy cold. Each comet analyzed gives us another piece of the puzzle of planetary formation, clues to how water was distributed, how organic molecules evolved, how quickly the Sun's materials mixed. It is as if the comets are libraries, each carrying a few pages of a very old book. By reading enough of them, we can reconstruct chapters of our own origins. This is why space agencies have made comets prime targets of exploration. Within their dust and ice are chapters of our cosmic history, waiting to be read. In the past few decades, humanity has reached out to these celestial archives with robotic emissaries, ushering in a golden age of modern comet exploration. No longer content to observe from afar, we have sent spacecraft to chase comets down, land on them, even pluck samples and return them to Earth. Each mission has revealed unprecedented wonders, peeling back layers of mystery. In 1986, when Comet Halley last visited, a fleet of probes swept by Halley's nucleus, capturing the first close-up images of a comet's heart. Those grainy photos astonished scientists. Halley's nucleus was a dark peanut-shaped rock, about 15 kilometers long, jetting out fountains of gas and dust. It confirmed the basic model of a dirty snowball, as astronomer Fred Whipple had poetically described comets. Fast forward to the new millennium, and our ambitions grew. In 2005, NASA's Deep Impact mission performed a bold experiment on Comet Tempel 1. It shot a 370-pound kg copper impactor into the onrushing comet, while the main spacecraft observed from a safe distance. On July 4, 2005, the impactor struck Tempel 1 at over 10 km/s, blasting out a brilliant explosion of material, a brilliant flash of light, as mission scientists described it, that later analysis showed was sunlight glinting off the plume of ice and dust flung from the comet's surface. For the first time, we had literally cracked open a comet to see what lies beneath its crust. The results from Deep Impact were revelatory. The impact kicked up fine powdery material, indicating that Tempel 1's interior is not solid rock or ice, but more like talcum powder or freshly fallen snow. A very fluffy structure, weaker than a bank of powdery snow. In fact, scientists concluded the comet might be 50th and 75% empty space inside, its ices and dust forming a loosely bound sponge. The plume analysis also detected a burst of organic compounds and carbon-rich dust. A huge increase of carbon containing materials was seen in the ejecta, showing that the comet's interior holds a substantial amount of organic matter. And within the dust, telescopes found microscopic clay and carbonate minerals, substances that form in liquid water, raising the puzzling possibility that liquid water had existed transiently inside or on Tempel 1. Deep Impact thus painted a picture of a comet as a fragile amalgam of primitive dust and ice, laden with organic molecules and even complex compounds, largely unaltered since the early solar system, except for a thin surface crust. It reinforced the idea that comets could have delivered organics to Earth by demonstrating the richness of organics beneath the surface. The mission also dramatically visualized how comets are eroded by each encounter with the Sun. One of the mission's key findings was that Tempel 1's interior ices are well shielded from sunlight by a layer of dust, meaning the deep interior could still harbor pristine ices from billions of years ago. Deep Impact's feat was not just scientific, but cinematic. Humanity punching a cosmic snowball to reveal its secrets, and it succeeded beyond expectation, confirming that much of a comet's story lies hidden just beneath a dusty veneer. Where Deep Impact blew a hole in a comet, NASA's Stardust mission delicately gathered pieces of one and brought them back to Earth. Launched in 1999, Stardust chased Comet Wild 2 and in 2004 flew through its coma, using an ingenious catcher made of aerogel to snag particles from the comet's tail. The spacecraft then turned around and delivered these particles to Earth in 2006, the first time we ever retrieved macroscopic samples from a comet. When scientists opened Stardust's sample canister, they found tiny scorched tracks in the aerogel, each made by a high-speed comet dust grain embedding itself. At the ends of some tracks, they found intact particles, giving us a direct, tangible piece of a comet to analyze in labs. The analysis was full of surprises. Wild 2's dust was a chemical kaleidoscope, abundant silicate minerals like olivine and pyroxene, mixed with truly primitive interstellar grains that predate the solar system. The comet was like a bag of trail mix, combining ingredients from all over the solar system. Most importantly, Stardust samples had a diverse suite of organic compounds, including a variety of carbon-based molecules, some akin to those seen in meteorites, but others unique. In 2009 came the dramatic announcement that glycine was positively identified in Stardust's return samples. It was the first direct proof of an amino acid in a comet, the first time an amino acid had been found in a comet, NASA noted, supporting the theory that some of life's ingredients were formed in space and delivered to Earth. The glycine in Wild 2 was likely formed by non-biological processes in the ice of the protosolar nebula, or even earlier in interstellar clouds. Yet here it was, preserved in a comet, and now in a dish on Earth. Stardust also found that Wild 2's makeup challenges the old simplistic notion that comets formed solely in the outer reaches. It suggested significant mixing of material across the young solar system. In essence, what Stardust brought back was a message in a bottle from 4.5 billion years ago, telling us that the nursery of the planets was a dynamic place where fiery and frosty materials commingled, and that comets carried an inventory of compounds relevant to both planetary geology and biochemistry. The success of Stardust was so great that the mission was extended to fly by Tempel 1 in 2011, interestingly, allowing us to see the crater that Deep Impact's impactor had made, and to observe how the surface had changed after one additional orbit around the Sun. Through Stardust, a literal piece of a comet lives in our laboratories, continuing to be studied with ever more advanced techniques and likely to yield insights for decades. It is as close as we've come to holding a comet's heart in our hands. Perhaps the most ambitious comet rendezvous was the European Space Agency's Rosetta mission. Launched in 2004, Rosetta spent 10 years cruising through space before softly catching up to Comet 67P Churyumov-Gerasimenko in 2014. When Rosetta arrived, 67P was still far from the Sun, a relatively inactive nucleus, which allowed the spacecraft to do something unprecedented: enter orbit around the comet. For over 2 years, Rosetta flew alongside 67P, observing it in exquisite detail as it warmed through perihelion and then cooled again. Rosetta became like a companion to the comet, a robotic witness to its entire cycle of awakening and slumber. The images it returned were breathtaking. 67P's nucleus was revealed as a bizarre rubber duck-shaped object with cliffs, plains, and towering jets spurting from pits. We saw the surface up close: cracked terrains, big boulders precariously balanced, and smooth dust covered basins. It was clear that even a small comet has a complex geological landscape, shaped by eons of sublimation and perhaps even episodes of fragmentation and re-merging. Rosetta's orbit sometimes brought it within a few kilometers of the surface, where it could practically taste the coma. Its instruments detected a veritable chemistry set around the comet. Not only the expected water, CO2, CO, but also molecular oxygen as mentioned, and a zoo of organics, acetylene, formaldehyde, methanol, and even more complex ones like amino acids and polyols. One of Rosetta's major findings was that 67P's water had a DH ratio 3 times that of Earth's oceans, casting doubt on the idea that comets like it brought most of Earth's water. But conversely, its detection of abundant organics, and even phosphorus, showed that comets are rich in life's ingredients. Rosetta also carried a small lander, Philae, which in November 2014 was released to land on 67P's surface, the first landing on a comet nucleus. In a dramatic series of events, Philae bounced and came to rest in a shadowed nook. In its short active time, Philae still managed to drill and sniff the comet's surface chemistry, detecting complex organic molecules, including 4 compounds never before detected on a comet, such as acetone and propionaldehyde. Though its battery died after a few days, Philae had already given us the first ground truth of a comet's surface, confirming it was a mixture of hard ice and dust with organics, and measuring its hardness and composition locally. Meanwhile, Rosetta kept orbiting and tracking changes, watching jets switch on, measuring how much mass the comet lost at perihelion, and then, as the comet receded from the Sun, observing the activity ebb. In September 2016, as 67P journeyed back outward, Rosetta gently descended to the comet's surface and joined it, a controlled landing that ended the mission. The wealth of data Rosetta returned has been transformational. We learned that cometary activity can create sinkholes and pits as subsurface ice pockets sublimate. We saw the day-night cycle of the comet driving regular water vapor pulses. Perhaps one of the most surprising Rosetta findings was the detection of large amounts of molecular oxygen, an unexpected guest, suggesting that 67P's ices formed in an environment that trapped O2, or that some reaction was producing O2 on the comet. Rosetta truly made 67P one of the most studied comets in history, turning it from a fuzzy dot in telescopes into a tangible world with its own character. By riding along with a comet, Rosetta fulfilled an old dream: to understand, from up close, how a comet lives and changes. It's as if for 2 years we had a seat on the comet's shoulder, watching it breathe and evolve. Rosetta's legacy is profound, not only in its scientific discoveries, but in cementing the idea that these icy wanderers are accessible places that we can explore directly, even land upon, as we would a moon or an asteroid. Just when we thought we had seen it all, nature delivered a completely unanticipated twist: comets from beyond our solar system. In 2017, astronomers detected a faint object on a hyperbolic path, meaning it was not bound to the sun, screaming through the inner solar system. Dubbed Oumuamua, it was the first confirmed interstellar object ever observed in our solar system. Unlike the comets we know, Oumuamua showed no visible coma or tail. It was more like a mysterious spindle. Its brightness fluctuated dramatically, suggesting an elongated or flat shape tumbling end over end. It passed closest to the sun and then headed out, exiting just as fast as it came. Only later did scientists realize it had a slight non-gravitational acceleration, as if something gave it an extra push. We got only a brief glimpse of Oumuamua, and it left more questions than answers. Was it a comet that had lost most of its volatiles? A shard of a shattered planetesimal from another star? A bizarre iceberg of pure hydrogen or nitrogen ice that outgassed invisibly? Its nature remains debated, an enduring mystery streaking between the stars. Then, in 2019, a second interstellar visitor was spotted, this time behaving much more like a normal comet. 2I Borisov, discovered by amateur astronomer Gennady Borisov, came in on a high-speed hyperbolic trajectory. Unlike Oumuamua, Borisov sported a palpable coma and tail. It was clearly an icy comet from another star, shedding gas and dust as it neared our sun. Astronomers were ecstatic. Here was a bona fide interstellar comet that we could study with our telescopes for months. And study it they did. Observations revealed that while Borisov looked similar to comets from our solar system, its composition had intriguing differences. In particular, Borisov was enriched in carbon monoxide. It had significantly more CO relative to water than any solar system comet observed at similar distance. CO is very volatile, sublimating at very low temperatures, so such a high concentration hinted that Borisov formed in an extremely cold environment, perhaps in the outer reaches of its home system around a cool, red dwarf star. One study even suggested Borisov might be a fragment from a Pluto-like dwarf planet orbiting another star, ejected during some collision event. Aside from CO, Borisov's makeup implied that chemically it wasn't entirely alien. It reinforced that the basic processes that make comets around other stars produce objects akin to those we know. Yet the differences, like the CO excess, are valuable clues to the diversity of planetary systems. As one astronomer remarked, an interstellar comet is like having a sample of another star's protoplanetary disk delivered to us. Borisov streaked through and was gone by 2020, but during its visit, we effectively had an emissary from an unknown solar system in our own backyard. These interstellar comets have broadened our perspective immensely. They confirm that small bodies roam interstellar space, likely ejected during the formation of planetary systems. They hint that the phenomena we observe in our comets, outgassing organic chemistry, are common in the galaxy, occurring around distant stars as well. Who knows what other exotic compositions or forms interstellar comets might have? We caught only 2. Statistics suggest there are countless more drifting between the stars, and we've just gained the capability to detect them. These alien messengers ignite our imagination. One day we might even send a probe to intercept one, to truly sample material from another star. For now, we use our best telescopes, like Hubble and ALMA, to glean what we can as they pass. In the silent rush of Borisov and Oumuamua, we felt the cosmic connection of distant worlds. They made the interstellar void just a bit more intimate, showing that nature flings pieces of worlds across the gulfs of space. A comet from a star 100 light years away might end up lighting our sky for a brief moment, a reminder that the story of comets is a galactic story, not just a solar system one. What does the future hold for comet science? It is an exciting time, for our tools and plans are evolving rapidly. Soon, an era of powerful survey telescopes will dramatically increase the discovery rate of new comets. The Vera C. Rubin Observatory in Chile, set to begin full operations in the mid-2020s, will scan the entire sky nightly with a huge camera. It's expected to find thousands of new comets, including many faint, distant ones that were previously missed. By one estimate, Rubin's 10th-year survey could quintuple the number of known objects in the solar system, effectively illuminating the population of distant long-period comets and maybe even catching incoming comets years before they reach the inner solar system. This means earlier warnings for any potential threats and more time to prepare missions to particularly interesting comets. Rubin might even catch the next interstellar visitor on its way in. Meanwhile, specialized spacecraft are on the horizon to meet comets on their own terms. The European Space Agency is developing Comet Interceptor, a mission scheduled for launch in 2029. Unlike previous missions that targeted known periodic comets, Comet Interceptor will wait at the Sun-Earth L2 point for a suitable target to appear. The idea is to be ready to ambush a truly new comet, ideally one making its first ever approach from the Oort cloud, or even an interstellar comet like Borisov. When such a pristine comet is discovered inbound, Comet Interceptor's trio of probes will deploy and fly by it, imaging it and sampling its environment in detail. This mission concept embraces the unpredictability of comets, essentially saying, we'll be ready when the cosmic dice roll a good one. On the sample, return front, scientists are eager to build on Stardust's success by bringing back a larger, more pristine sample of a comet, including volatile ices. A proposal called Caesar was developed to revisit Comet 67P and collect at least 100 grams of material, carefully isolating the volatiles so that even the sublimation gases could be returned in a sealed container. Though not yet funded, Caesar or similar concepts remain high on the wish list because having a well-preserved chunk of a comet's nucleus in terrestrial labs could revolutionize our understanding of comet chemistry. We would be able to analyze amino acids for chirality, search for complex organics, and perhaps even prebiotic compounds with the full power of modern analytical chemistry, and precisely date grain components to see if some predate the solar system. Future mission planners also dream of landing on a comet again, this time with rovers or hoppers that could explore multiple sites, or even drilling into a comet to bring up samples from a meter or two down. Technologically, this is challenging. Comet surfaces are low, gravity, uneven, and active, but not impossible. There's also talk of missions to special comets like Main, belt comets. In fact, the James Webb Space Telescope recently detected water vapor from a Main belt comet, confirming that water ice can survive in that region. With Webb's keen infrared eyes, astronomers can now study the outgassing of comets in unprecedented detail, even when the comets are far from Earth or faint. Webb and its successors will examine the molecular makeup of comet comas, detecting trace species and isotopes that ground telescopes struggle to see. All these developments, better surveys, agile interception missions, advanced sample returns, and powerful space telescopes are converging to ensure that the next decades will be a renaissance in cometary science. We stand to answer some burning questions. How do comet nuclei structurally differ? What precise recipes of organic chemistry do they carry? And could those have led to life's emergence on Earth? How do comet populations in other star systems compare to ours? Are there many Borisovs out there with exotic compositions? Are there detectable patterns in comet orbits that hint at undiscovered distant planets? Each new comet observed or visited is another data point in unraveling these mysteries. Even as we peer ahead, comets remind us of the cyclical nature of time and the grace of celestial mechanics. Some comets are periodic. They return on regular schedules, their orbits bound to the sun in ellipses like cosmic clockwork. Halley's Comet, for instance, completes an orbit about every 76 years, faithfully revisiting the inner solar system as generations of humans pass. It is a periodic comet of the Halley type class, meaning its path is elongated and inclined, taking it far beyond Neptune before swinging back around. Halley has been observed since antiquity. Each return, it has been noted by those who knew to expect it, or feared it as an unpredictable omen in older times. It will return again in 2061, completing yet another cycle in its millennia, spanning journey. Many other comets belong to Jupiter's family, like Comet Encke, which whips around the Sun every 3.3 years, the shortest orbit of any known comet. Encke's frequent returns make it a familiar, if modest, comet. Its orbit is tightly bound near the inner planets, likely shaped by past interactions with Jupiter that captured it into a smaller loop. On the other extreme are long, period comets, those that take thousands or millions of years to return, or may be visiting the inner solar system for the first and last time, if their orbit is open. These come screaming in from the Oort cloud with orbital periods so long, they effectively appear just once from humanity's perspective. Some long-period comets might be on bound orbits of, say, 100,000 years, but others, after slinging around the Sun, get flung out entirely, either by gaining energy from a planetary encounter or by having come in on a trajectory that wasn't bound in the first place. In a sense, each comet's fate is written by gravity, by the immutable equations of orbital dynamics and the chance encounters it experiences. A periodic comet, like Encke, found a stable niche and will likely keep cycling until it gradually evaporates away or a perturbation kicks it out. A comet, like C2012S1, was likely a first-time visitor from the Oort cloud. It dived near the Sun and disintegrated, its fragments carried off on hyperbolic escape paths, never to return. The cycles can also evolve. A long-period comet might be captured into a shorter period by a lucky interaction with Jupiter, or a periodic comet might get tossed out by a similar encounter. One famous example, Comet Brooks 2 in 1886, had a close brush with Jupiter that radically changed its orbit, essentially capturing it into a new, shorter period. Conversely, Lexell's comet in 1770 passed extremely close to Earth, and then, after 2 apparitions, passed near Jupiter and was ejected from the inner solar system entirely, never seen again. Gravity giveth and gravity taketh away. Over time, periodic comets also evolve physically. Each passage by the Sun costs them some mass, like a spoon of ice cream melting off with each lick of heat. Eventually, many periodic comets likely fizzle out or break apart. Halley's Comet, for example, has been losing mass for thousands of orbits. Scientists estimate its nucleus has eroded considerably and may survive only another few thousand revolutions before it becomes an inert husk or vanishes in a spray of debris. In a sense, comets have life cycles, a birth, a long dormancy, a potential series of active apparitions, and a death either by evaporation, disintegration, or collision. Some comets die spectacularly, like Comet Shoemaker, Levy 9 did by impact, or like Comet Ison, which evaporated in the Sun's corona, while others simply fade to black, their volatiles exhausted, so they no longer grow comas, but persist as dark, rocky objects akin to asteroids. It's thought that a number of near-Earth asteroids might actually be extinct comet nuclei, the remains of comets that died after many orbits of activity. For example, asteroid 14827 Hypnos and others show characteristics hinting they could be spent comets. Even Encke's comet itself has much lower activity than one would expect for its size, suggesting it's nearing exhaustion, shedding less material each pass. The torrid meteor showers that grace our skies every year in late October and early November are attributed to debris from Comet Encke's gradual decay. This meteor stream contains not just dust, but possibly larger fragments. Indeed, there's speculation that some Tunguska-sized objects in the torrid swarm are leftover pieces of Encke's parent body, hinting that Encke may be the remnant of a much larger comet that fragmented ages ago. All these patterns, capture, loss, fragmentation, periodicity, illustrate that comets, for all their wandering, follow the rhythms set by gravity. In their paths, we see the fingerprints of planets and forces that have shepherded them. Each comet's orbit is a story of where it came from and what it encountered. Some are near, parabolic, whispering of origins in the dark Oort cloud. Some are tightly elliptical in the plane of the ecliptic, betraying a past in the Kuiper belt or scattered disk. Some, like Halley, have retrograde or inclined orbits, suggesting they were tossed in from the Oort cloud, yet bound to return. Each path is an archive of gravitational interactions. It's humbling that even such seemingly erratic travelers obey the same physical laws that guide planets in their courses. The difference is that comets have 1 foot in Newton's clockwork and 1 foot in chaos. Their fates can pivot with a chance encounter. Thus, they symbolize both the predictability and the caprice of the cosmos. Through all these scientific lenses, however, a comet is more than just a subject of study. For those who stand under a clear night sky and witness a great comet arcing overhead, there is an undeniable emotional and philosophical impact. Comets have forever been omens and inspiration, provoking fear and wonder in equal measure. In ancient times, they were often seen as divine messages, the harbingers of doom, as many cultures called them. Their sudden appearance, unpredictability, and striking form set them apart from the regular stars and planets, which moved in reassuring order. To people who didn't know where comets came from, it was natural to imagine they were sent by gods or spirits. One culture might see in the comet's tail the flowing hair of a weeping woman, a celestial mourner heralding sorrow. Another might see a fiery sword blazing across the heavens, an unmistakable sign of war and wrath from the gods. The ancient Chinese called comets broom stars and long-tailed pheasant stars, and painstakingly recorded their appearances and how their tails pointed, interpreting them as portents of imperial fortunes. A comet, seen in 1066, was recorded in the Anglo-Saxon Chronicle as a fearsome sign. Indeed, that year saw the Battle of Hastings, and the famous Bayeux tapestry depicts the comet with people staring and pointing, captioned Isti mirant stellum. These men marvel at the star, which they believed heralded the fall of King Harold and the rise of William the Conqueror. Across cultures, the word disaster literally means bad star, from Latin dis, astrum, reflecting the belief that an ill-omened star brought calamity. Even as late as 1910, when Halley's comet returned, despite humanity's strides in understanding, a wave of public fear swept through because spectroscopes found toxic cyanogen gas in the comet's tail, and newspapers sensationally claimed Earth would be poisoned as we passed through it. People bought gas masks and anti-comet pills in panic, though scientists reassured that the gas was far too rarefied to have any effect. Comets have thus been mirrors for human emotions, fear of the unknown, the need to find meaning in the unpredictable. But they have also been viewed with awe and curiosity. Not all cometary omens were negative. Some ancient societies saw them as heralds of change that could be positive or at least significant. And in the Renaissance, as understanding grew, comets became objects of fascination for early scientists. like Tycho Brahe and later Newton and Halley. The transition from superstition to science in comet study is one of the triumphs of human intellect, yet even now, knowing what they are, we can still feel the mythic resonance when we see one. There is something poetic about a glowing traveler appearing unannounced, silently traversing the night, and then disappearing into the dark again. We can empathize with our ancestors. A bright comet in ancient skies must have felt like a rupture in the normal order of things, a moment when heaven's script flipped to a new page. Even today, a great comet can unite global audiences in shared wonder. In 1997, Comet Hale, Bop hung in the sky for months, so bright it was visible even above cities. It became a cultural phenomenon in a quiet, uplifting way. Millions of people, regardless of nationality or belief, gazed up at its jewel tails night after night, reminded that we all share the same sky. Comets thus have a unifying quality too. They prompt us to look upward and outward, to ponder our place in the universe. They are emblems of impermanence and renewal. Each comet's apparition is fleeting on the human scale, a matter of days or weeks of peak display. Yet the comet itself endures on a much longer orbital cycle, or if not, its materials disperse and perhaps seed new worlds. Watching a comet, one senses the slow ticking of cosmic time. The comet may have last visited before we were born and will return long after we are gone. In that realization is a humbling truth. Our lives are brief, and these celestial events link generations separated by centuries. A person in ancient China who noted a comet on a bamboo chronicle, a medieval monk who painted a comet in the margins of a manuscript, a modern child who makes a wish under a comet's tail, all connected by these passing cosmic hikers that journey between the ages. There's also a gentle existential lesson: fragility. The comet's beauty is born of its disintegration. It must lose itself to become the vision we adore. As it sheds those tails, it is gradually consumed. Nothing in this universe, not even a lovely comet, lasts forever. Halley's Comet, blazing through history, is slowly dying with each passage, its mass whittled away. One day, it will be gone. But new comets will take its place, falling in from the reservoir at the solar system's edge. Thus, comets embody the cycle of death and rebirth on a cosmic scale. They hint that creation and destruction are partners. The water that comets spend into space might become part of a new planet's ocean. The organics they scatter could seed fledgling life elsewhere. A comet's life and death are part of a grander continuum of matter. For those given to reflection, seeing a comet can feel like touching the infinite and the ephemeral at once. Its glowing form against the starry background speaks of beauty, unearthly, unowned, freely given, and of transience, because you know it will not last. Perhaps this is why comets have inspired so much art, poetry, and even religion. They provoke wonder about the workings of the heavens and introspection about our own lives. Mark Twain, who was born under Halley's Comet in 1835, famously mused that he expected to go out with it in 1910, and indeed, he died one day after Halley's perihelion that year. He saw the comet as a cosmic bookmark to his life, a personal omen in a scientific age. Such is the hold a comet can have on the human psyche. Now, the comet we have been following has looped around the sun. Surviving its blistering approach, it is outbound once more, its tails fading as the icy fountains weaken. We imagine ourselves riding with it briefly as it recedes. The sun grows smaller. The great gaseous trails that made it magnificent are dissipating into space, left behind as a transient trace of its journey. Before long, the coma will collapse back onto the surface. The comet will become a quiet, solid traveler again. It returns to the cold depths, carrying perhaps a thin mantle of fresh dust from its recent activity. Slightly altered, but still essentially the same nucleus forged eons ago. In the skies of Earth, the once splendid comet is now barely a smudge in telescopes, then not even that. To the naked eye, it is gone. The show is over, the cosmic stage empty once more. But the memory remains, in photographs, in data, and in the minds of those who looked up and felt a connection with something beyond the ordinary. The night after a bright comet disappears feels a little emptier, as if a friend has departed on a long voyage. Yet there is also a sense of gratitude and privilege at having witnessed one of nature's most sublime performances. The sky returns to darkness and silence. Stars wheel in their eternal courses. All seems as it was. But we know that somewhere out there, far beyond our sight, that comet continues its journey. Perhaps it will circle back decades or millennia hence, or perhaps it will wander interstellar space forever. And we know too that elsewhere, other comets are inbound, unseen as yet. The great vault of the Oort cloud still holds countless icy nomads awaiting their call. The Kuiper belt at the fringe of Neptune's realm steadily feeds short-period comets inward. Even now, dozens of comets traverse the solar system in various stages of their lives, most faint and unnoticed except by astronomers. The cosmos is never truly still. There is always motion, always a story unfolding, often out of sight. Under a moonless night, an observer on Earth gazes at the horizon where a comet once glowed. Now there is darkness. But that darkness is not empty. It is filled with possibility. The observer might recall how just weeks ago, a brilliant tail stretched there and feel a poignant longing. Comets remind us of how rare and precious some sights are, how we must cherish them when they arrive. They also remind us of the vastness of time. We may wait a lifetime to see a great comet, or we might be lucky to see several. It is not for us to command, only to appreciate. And in waiting, we participate in an age, old human experience, sky-watching with hope and humility. In the stillness of the pre-dawn hours, the world turns and a new day's light creeps in. The comet's memory melds into the growing glow of sunrise. Yet, somewhere, a comet moves. Perhaps it's our comet of focus, now far away, retreating into solitude with a dwindling tail still gently pushed by the solar wind. Perhaps it's another, just now beginning to feel the first whispers of the sun and growing a tenuous halo in reply. The cycle continues unbroken. One day, another distant glimmer will appear in our telescopes, another celestial visitor announcing itself in the silent language of reflected sunlight. And humanity will aim its curious eyes and instruments at it, studying it, admiring it, wondering about it. The horizon is never truly empty. It is an endless watchtower for the next marvel to rise. In the final meditation of this journey, we return to the image of a lone comet sailing through space. Envision it in the darkness, a tiny nucleus of ice and dust, perhaps peppered with rocky bits, with a faint aura around it, the last vestige of its coma gradually dispersing. It is quiet now, after the frenetic activity near the sun. It has shed material, but it has also gained something intangible, another chapter in its existence, another imprint on the universe. Ahead of it lies a long arc into the outer solar system. Decades, centuries, or millennia from now, it may reach its farthest point and begin falling inward all over again, or it may escape to the stars, never to return. But at this moment, as it moves away from the sun, there is peace. The comet is alone with its ancient memories. The stars around it are the same that shone when it first formed. The sun, now distant, gently pulls it along a precise path defined by gravity and momentum, a path that is part of the grand design of our solar system. We on Earth continue about our lives, but that comet and others like it persist on the margins of our awareness. They are like the background music of the solar system, usually quiet, occasionally swelling into a crescendo that demands attention. Knowing they are there enriches our view of the cosmos. For beyond the planets and their moons, beyond the asteroid belts and rings, there is this community of nomads that connect the solar system's fringes to its heart. They remind us that the solar system is not static. It has interchange and traffic, a circulation of material. They are messengers carrying water and organics from one realm to another. They are storytellers that can speak of the past and perhaps carry messages to the future. The sky tonight holds no obvious comet, yet someone with a telescope might find a faint one in Cancer or Hydra, a small fuzzy patch that is the only hint of an ongoing miracle. The rest of us wait until the next bright one graces us, and when it does, we will once again stand under the night, perhaps on a cool evening or crisp morning, and watch a silver, blue, or golden tail etched against the stars. We will feel the ancient stirrings that comets evoke, a mix of wonder, a touch of worry, a deep curiosity. We will perhaps whisper to a friend or child, "Look, a comet," joining our voice to a lineage of sky watchers going back to the dawn of our species. The comet will silently arc onward, impervious to our awe, yet somehow giving meaning to it. In the quiet, after the comet's passing, we understand something fundamental. We are part of a universe of cycles and journeys. Our own existence, so brief and small against the cosmic scale, is nonetheless connected to these grand events. The water in our bodies may have been delivered by a comet billions of years ago. The carbon in our DNA could be the very carbon that spent time in a comet's nucleus before becoming part of Earth. We observe the comet externally, but internally, we resonate with it, perhaps because we carry a bit of that stardust within us. The comets, in their peregrinations, illustrate the concept of cosmic impermanence and renewal. Things change, yet some patterns endure. They perish, yet from their remnants new structures can form. In that way, nothing is truly lost, only transformed. The horizon brightens further, dawn is near. Our imaginary comet friend is now far beyond human sight, but we know it moves on. The stars fade one by one as sunlight paints the sky. The earth spins toward day, and life goes on under the blue vault, largely oblivious to the celestial dramas overhead. But when dusk comes again and stars peek out, who knows? Perhaps a new visitor will have appeared. We live in expectancy and hope for such moments. Comets have been and will be with us for as long as humanity can look up. They are a bridge between the finite and the infinite, a reminder that while we are tiny, we are also part of something vast and beautiful. In the stillness after the celestial spectacle, one can almost hear the echo of what the comet has whispered. Remember me. Remember this feeling. We are all part of the same story. The sky is quiet now, but beyond the edge of sight, in the great dark between the stars, a spark of ice and dust continues on its way, carrying a tale as old as the solar system, headed for destinations unknown. It moves through the shadow with silent purpose, a wanderer forever. And somewhere, sometime, when the moment is right, it, or one like it, will return, igniting the night once more with its fleeting glory, and the cycle of wonder will begin again. Each ending is a new beginning in the story of comets. The horizon waits. Somewhere, a comet moves. In the beginning, there is nothing but darkness. For ages untold, after the birth of the universe, there is no light, only a silent void and the cooling embers of the Big Bang. Imagine this primordial darkness. No stars, no galaxies, just an endless night stretching millions of years. Yet in that darkness, something is stirring. Gravity is gently pulling together clouds of pristine hydrogen gas, gathering and squeezing them in invisible hands. Deep in one such cloud, pressure mounts, atoms collide, and heat rises. There is a tremor in the void, a hint of radiance forming, still hidden. Then, suddenly, light. A blinding spark erupts where there was none before. In an instant, the first star ignites. The cosmic dark ages end in a flood of starlight. It is the universe's first sunrise. A lone star has begun to shine, pouring out photons into the black abyss. Soon, another star kindles, and another. The newborn cosmos sprinkles itself with tiny islands of light. The darkness of creation is pushed back by these early fires, and the cosmic dawn has arrived. What was once cold and black is now dappled with the warm glow of starlight. Eons later, on a small young planet orbiting a later generation of those stars, there comes another first sunrise. Picture Earth over 4 billion years ago, a barren world of rock and boiling seas under a choking sky. The air is thick with volcanic fumes and the dust of creation. As the planet cools, its skies begin to clear. One morning, the clouds part to reveal a brilliant glow on the horizon. Dawn breaks over Earth's primordial landscape. For the first time, sunlight bathes the craters and steaming oceans of our world. The infant sun climbs over the horizon, and day begins on Earth. The planet's surface, once lit only by lava and lightning, now knows the gentle illumination of a star. That first sunrise would have been an alien scene. No life to witness it. Only chemistry and stone. Yet it was a harbinger. From that day onward, every living creature on Earth would be born to a world warmed and lit by a star in the sky. Our sun had arrived in our heavens, and nothing would ever be the same. Ancient reverence. From the moment humans first opened their eyes under its golden light, we have felt the sun's power. Long before science, we knew in our bones that our lives depended on that glowing orb. Every dawn brought light and warmth. Every dusk brought its absence. In the sun's daily rising and setting, ancient peoples saw the dance of gods and the rhythm of existence. So across cultures and centuries, mythologies blossomed around the sun. Our star became our deity, our timekeeper, our source of life in story and song. In ancient Egypt, the sun was Ra, the falcon-headed god who sailed across the sky by day in a great barge and descended into the underworld at night. Each sunrise was Ra's triumphant return after vanquishing the darkness. Egyptians tilted their faces to the dawn and felt the touch of a divine father. Far to the east, Vedic hymns of India praised Surya, riding a chariot led by 7 shining horses, bringing light, dispelling evil, and watching over all creatures. In the clear air of the Andes, the Inca honored Inti, the radiant patron of empire, believed to be an ancestor of their kings. Temples and treasures were devoted to Inti's glory. The sun's daily journey inspired vivid imagination. The Greeks envisioned Helios, a titan crowned with rays, steering a fiery chariot drawn by stallions across the sky from east to west. Each evening, Helios would descend at the horizon and embark on a nightly voyage in a golden cup back to the east, so he might rise again. His Roman counterpart Sol, and later Sol Invictus, the unconquered sun, symbolized continuity and victory over darkness. In Japan, the sun was personified as Amaterasu, the great goddess of light. When she hid herself in a cave out of grief, the world was plunged into darkness until the other gods lured her out, restoring light and hope. Every culture found its own language for the sun's gift. The Norse spoke of the goddess Sol, forever chased by a giant wolf across the sky. At the end of days, they feared the wolf would catch her, and darkness would consume the world. The Aztecs offered beating hearts to Tonatiuh, the sun of the 5th age, believing only constant sacrifice could fuel the sun's strength to rise each day. In Mesopotamia, mighty Shamash not only lit the day, but also saw all, becoming a god of justice, shining his light on the truth. The Chinese told of 10 suns that once scorched the world until only one was left to give gentle light. the sun has been a wheel of fire, an eye in the sky, a divine torch carried by various hands in human imagination. We built monuments to chase the sun's movements. On Salisbury Plain, Stonehenge's stones were carefully aligned with the solstice sunrise, so the first ray on midsummer's morning would pierce straight to the heart of the circle. In temples and pyramids across the world, from Abu Simbel in Egypt to Angkor Wat in Cambodia, architects aligned doorways with the sun, capturing its light on sacred altars on specific days of the year. To ancient peoples, these moments when the sun's light perfectly struck their creations felt like communion with the heavens. The sun told them when to sow and when to reap, marking seasons with its ever-changing arc in the sky. A stable sun meant abundance. An eclipse or an unexplained dimming could instill terror that the gods were angry or the end was nigh. In prayer, in ritual, in art, humanity paid homage to this bringer of life. We bowed to dawn and rested at dusk. We celebrated the sun's return at winter solstice festivals, when days would lengthen again. Even monotheistic religions kept echoes of sun worship, halos around saintly heads, Sunday as a holy day. The sun was our first clock and calendar, a golden heartbeat to measure our days. Yet, for all its importance, the true nature of the sun remained a mystery to our ancestors. They saw a bright disk that moved and gave heat, but what it was, a chariot wheel, an eye of a god, a hole into the realm of fire. No one knew. Still, they revered it rightly as the great sustainer. They intuited that without the sun's daily presence, the world would be cold and dead. In their myths, the sun was often benevolent, but sometimes fickle or wrathful, a reflection of how its light could bless crops or, in drought, become a searing curse. Even today, if you've ever stood at dawn and felt the first rays warm your face, you can sense that ancient awe. The sun touches something primal in us. It's no wonder early humans worshipped it. They were reaching out to understand and thank the very thing that made their lives possible, from myth to science. In time, humanity's curiosity outgrew our myths. We began to seek a more concrete understanding of the sun. Gazing up, we asked not only who carries the sun across the sky, but what is the sun, really? Our journey to the answer spanned centuries. It led us from seeing the sun as a unique heavenly jewel to recognizing it as one among countless stars, and ultimately to uncovering the nuclear fire at its heart. It started with a radical idea, that the sun, not Earth, was the center of things. Renaissance astronomers like Copernicus and Galileo dared to put the sun at the center of our solar system, dethroning Earth. This heliocentric model slowly overturned old cosmic orders, and with them, the special pedestal of our sun as something apart from the stars. In 1610, Galileo turned his telescope to the sun and saw dark blemishes crossing its face. Sunspots. The discovery that the sun had spots, and that they moved, showing the sun's rotation, was shocking. It meant our perfect heavenly light had imperfections. The sun was not a flawless god, but a dynamic, changing sphere. Galileo's observations, nearly blinding work in an era without proper filters, marked humanity's first scientific look at our star. As the centuries turned, more questions arose. What was the sun made of? How could it burn so brightly for so long? By the 19th century, even as scientists catalogued the sun's spectrum and found new elements, the sun's power source remained an enigma. Some theorized it was a burning coal or contracting gas, but calculations showed chemical fire or gravity alone could not sustain the sun for millions of years, let alone the billions required by Earth's geology. The sun simply put out too much energy. The answer arrived in the 20th century. The sun shines by thermonuclear fusion. In its core, light elements are fused into heavier ones, releasing prodigious energy. In essence, the sun is a gigantic nuclear reactor. This realization dawned slowly. Scientists like Arthur Eddington first guessed it, that the pressures at the sun's center could force hydrogen atoms to merge into helium. Later, others worked out the details of those reactions. At long last, we understood. The sun was not a divine flame or a burning ember of creation. It was a star, a common type of star, powered by extraordinary processes. The gulf between our sun and the stars in the night sky closed. They were the same kind of thing. Our sun is just our star, the one we happen to live next to. This was a humbling shift. The sun went from being the singular light of our existence to one of perhaps 100 billion lights in our galaxy. The word sun itself simply means any star that has planets in orbit. Astronomy taught us that each star in the sky is another sun for someone, and perhaps each sun in turn could warm other worlds. The universe became both bigger and more intimate. We found kinship between our sun and the countless stars shining out there. So our sun is a typical star, but it is also unique to us. It is our sun, the anchor of our solar system, the gravitational linchpin that holds 8 planets, dozens of dwarf planets, millions of asteroids, and trillions of comets in its family. It contains 99.8% of all the mass in the solar system. All the planets, moons, and debris are mere crumbs from the sun's table. This brilliant sphere dominates our cosmic neighborhood. Today, instead of worship, we show reverence through exploration. We study the sun with a fleet of spacecraft and a cadre of telescopes. We have learned more in the last few decades than in all of human history before. Yet the more we uncover its scientific secrets, the more our sense of wonder grows. The sun is not a simple ball of fire. It is a complex living system with a heartbeat and moods, with mysteries and surprises still in store. We have traded mythic poetry for factual poetry, one might say. The truth of the sun, as a star powered by fusion, variable and even violent, is as awe-inspiring as any legend. With our modern understanding, we can tell the sun's story from its birth among the stars, through its present life, giving glow, and on to its far future fate. We can connect the nuclear reactions in its core to the warmth on our skin. We can appreciate how the sun's tantrums create ethereal auroras on Earth, and how, someday, the sun will transform and force life as we know it to change or perish. This is the saga of our sun, one star in an endless sea, yet everything to us. Now, let us journey into the life of the sun itself. Let us peel back the layers of our star, travel to its core, and ride the energy outward. We will watch the sun's surface seethe and erupt. We'll follow its influence across space to Earth and beyond. We'll look back to the sun's birth and forward to its death. And in doing so, perhaps we'll come to see the connection between that nuclear furnace and the beat of our own hearts, born of cosmic clouds. Every star has a story that begins in darkness. The sun's tail starts around 4.6 billion years ago in a cold, diffuse cloud of gas and dust on the outskirts of the Milky Way galaxy. Picture a vast nebula, light years across, full of hydrogen, helium, and faint traces of heavier elements. For ages, this cloud drifted quietly. Then something happened to disturb its peace. Perhaps a shockwave from a distant supernova slammed into it, or maybe 2 clouds collided. Whatever the trigger, it caused a region of the cloud to compress. Within that region, gravity took hold. A denser clump drew in more and more material, growing denser and heavier in a runaway process. As the gas fell inward, it began to spin, an ice skater pulling in her arms, rotating faster and faster. The collapsing clump flattened into a swirling protoplanetary disk, like a cosmic whirlpool, with most of the mass collecting at the center. That center grew ever hotter and denser as gas piled on. This was the protostar that would become our sun, still shrouded, not yet shining by its own light, but getting warmer and warmer. Around this infant protostar, the remaining disk of gas and dust would eventually clump to form planets, moons, and asteroids, the embryonic solar system. But at this early stage, all attention is on the burgeoning star, child, at the disk's core. As more mass crushed in, the protostar's core pressure skyrocketed. When the core reached about 15 million degrees Celsius, a profound transformation occurred. Hydrogen nuclei began to fuse. At first, it was just a trickle of fusion reactions sparking to life, but soon a threshold was crossed. The protostar effectively ignited in a sustained way. The inward crush of gravity was met by the explosive outward pressure of new energy. The darkness of the collapsing cloud was pierced by the first true starlight of our sun. It was born, a full-fledged star, now stabilizing into the long, steady burn of its youth. If we could have witnessed it then, we'd see a new star appearing where none had shone before, hidden deep in its natal cloud until its light blew away the cocoon. Perhaps it glowed a bit bluer and larger at first, shedding excess heat, then settled to the yellow-white we know. Our sun joined the cosmic landscape as one more pinprick of light in the galaxy. Around it, the leftover disk began to cool and condense. Within tens of millions of years, that disk formed the planets, including Earth, making the sun not only a star, but the center of a solar system. Interestingly, our sun wasn't born alone. Star formation often happens in clusters. Multiple stars form from different clumps in the same giant cloud. Our sun likely had sibling stars, born in the same stellar nursery. For a few 100 million years, they might have been loosely bound, a cluster of suns drifting together. But over time, they scattered across the Milky Way, each going its own way. Somewhere out there in the galaxy, far from us now, there may be stars that once twinkled alongside the infant sun before destiny separated them. Now they are just anonymous stars in the night sky, their shared origin with our sun obscured by time and distance. So the sun's birth was both a solitary emergence from darkness and part of a communal genesis of many stars. From gravity's pull and nature's want of equilibrium, a star was born, the furnace was lit, and in that lighting, the stage was set for everything to come, the formation of Earth and the eventual spark of life in the sun's warm glow. The hearth of fusion, at the core of the newborn sun, and still today, in the mature sun, an astonishing process unfolds: thermonuclear fusion. This is the engine of the star, the secret of sunlight. Yet for all its technical sound, we can think of fusion in human terms. It is the sun's heartbeat, the rhythmic source of energy that keeps it alive. Deep in the sun's center, the conditions are almost inconceivable. The pressure is millions of times the atmospheric pressure on Earth. The temperature is around 15 million degrees C. The hydrogen gas that composes most of the sun is crushed so tightly that it becomes a dense plasma, atoms stripped of electrons, nuclei packed shoulder to shoulder. In this extreme environment, hydrogen nuclei, which are simply protons, are forced close enough together to overcome their natural repulsion. When two protons slam together hard enough, they can stick and transform, ultimately creating a helium nucleus out of 4 hydrogen nuclei through a series of reactions. In that alchemy, a tiny bit of mass is lost and converted to pure energy. This is happening constantly, in a chain reaction known as the proton fusion cycle. Every second, the sun's core fuses about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, converted to energy as radiant light and heat that eventually makes its way out of the sun. 4 million tons of matter turned into energy every single second. It's a number almost too large to grasp. It's like detonating billions of nuclear bombs each second just to produce the sunlight we find so gentle here on Earth. How can we imagine this furnace? Perhaps as a stellar heart, throbbing out energy. or as a vast forge where the simplest element, hydrogen, is forged into helium, like an eternal smithy. Or think of it as a boiling cauldron of creation, where matter and energy are freely interchangeable. The core is only about a quarter of the sun's radius, but it holds nearly half the sun's mass, densely packed and actively burning. It is here that the sun's life is decided. So long as there is hydrogen to fuse, the sun will shine steadily. Fusion in the sun is a surprisingly subtle dance, not a runaway explosion. The star's self, gravity contains and regulates it. If the core produces a bit too much energy, the core will expand slightly, cooling and slowing the fusion rate. If it produces too little, the core contracts, heating up and boosting fusion. This feedback keeps the sun in an equilibrium that has persisted for billions of years. In this way, the sun is stable, a gently humming engine rather than a bomb. The heat flowing outward provides pressure to counter gravity inward. A beautiful balance. Gravity compresses, fusion energizes. One tries to collapse the star, the other tries to blow it apart, and in the middle the sun holds steady, like a suspended ball in a fountain stream. While hydrogen fuses to helium in the core itself slowly accumulates helium ash. Over the sun's lifetime, helium has been building up inside. But the sun has so much hydrogen and burns it relatively slowly that even after 4.6 billion years, it's nowhere near running out. Our sun is comfortably middle-aged, still rich in fuel for about another 5 billion years of hydrogen burning. It's mesmerizing to think. Every photon of sunlight, every beam that warms your skin began as an act of nuclear fusion in the sun's core. Each one was born in a flash of two atoms becoming one, releasing energy. The sunlight is literally the product of mass turned into energy deep within our star. The sun's core is a closed realm, hidden from direct view. Yet it is the very definition of vitality for the sun. If we call the sun the heart of our solar system, it's apt because within the sun lies a heart of its own, pumping out the light that feeds the planets. This fusion hearth is not static. It subtly pulses, not in dramatic throbs, but through waves and oscillations that ring through its interior. Through a field called helioseismology, scientists have detected sound waves echoing inside the sun, caused by bubbling convection and other processes. By studying these solar seismic waves at the surface, we infer details about the core's conditions. In essence, we can listen to the sun's heartbeat and learn its rhythm and structure. It's like ultrasound for a star, listening to its ringing to map its insides. And what have we found? That the sun's core rotates a bit faster than its surface, and that it's maybe a touch hotter or cooler in spots than expected, but by and large, our models of fusion hold true. With the core burning steadily, the sun has entered what's known as the main sequence phase of its life, the long, stable period in which a star fuses hydrogen to helium. For a star of the sun's mass, this period lasts about 10 billion years. Our sun is nearly halfway through that allotment. During this time, it changes only gradually, growing slightly brighter over eons as helium accumulates in the core. But for now, the sun shines with a steady golden consistency that has nurtured life on at least one world. Journey of light. Consider now a single photon, a particle of light, born in the sun's core. It begins its life as a high-energy gamma ray emitted from a fusion reaction. In that first moment, it's a blazing bit of energy flying outward, but its journey to escape the sun is anything but straightforward. The sun is incredibly dense in its interior, and this newborn photon's path is immediately halted by a collision with a nearby proton or electron. It gets absorbed and re-emitted or scattered in a random direction. It zigzags and ricochets through the crowded interior like a pinball in an infinite machine. The sun's interior has layers like an onion. From the core out to about 70% of the sun's radius lies the radiative zone. Here, the dominant mode of energy transfer is by radiation, photons carrying energy outward, but it is a slow diffusion process. The photon we imagined will undergo an enormous number of scatterings in the radiative zone. It bounces a short distance, hits a particle, gets sent in a new direction, maybe even back inward, then out again, over and over. It performs a drunken, random walk toward the surface. The distances between collisions grow longer as the gas gets thinner farther out, perhaps only a fraction of a millimeter near the core between collisions, stretching to a few centimeters near the radiative zone's outer edge. It is an epic and tedious journey. How long does it take for a photon to get out? Ironically, something that travels at the speed of light can take on the order of thousands or even hundreds of thousands of years to escape the sun. Estimates vary, but by many accounts, the sunlight that reaches your eye today began its trip in the sun's heart when humanity was in its infancy or before. In a poetic sense, the daylight illuminating an ancient Egyptian carving might have been generated around the time the sun's energy currently warming us was starting its long march outward. The sunlight is ancient by the time it emerges. In contrast, once it's free, it only takes a brief 8-minute sprint across space to reach Earth. Thus we say, every sunrise is powered by ancient light. Eventually, our photon reaches the outer 30% of the sun's interior, the convection zone. Here, the density has dropped and the temperature gradient steepened such that gases can't transfer heat by radiation alone. They begin to circulate like a boiling pot of water. Hot plasma near the radiative zone rises toward the surface, cooling as it goes, then sinks once it has given off its heat, only to be reheated and rise again. These convection currents are enormous, each cell the size of a continent or larger. In cross-section, they look like granules or kernels. Indeed, if you look at the sun's surface with a high-powered telescope, you see a granulation pattern, a carpet of bright blotches with darker boundaries. Those bright blotches are the hot tops of convection cells where material is upwelling. The dark outlines are cooler, sinking material. The scale is staggering. Individual granules are on the order of 1,000 kilometers across. For our photon, being caught in the convection zone is like catching an express elevator after wandering in a maze. The energy gets swept up by the moving plasma and ferried upward much more directly. Within days or weeks, a blob of plasma can rise from the bottom of the convection zone to the visible surface, carrying its photon energy with it. When that plasma finally reaches the surface, the photosphere, it radiates the energy away as new photons of mostly visible light. Our original photon might have been absorbed and its energy redistributed into many lower energy photons by now. By the time energy leaves the sun, it is mostly in the form of visible light with a spectrum peaking in the greenish yellow, perfect for our eyes, which evolved under this light. In essence, the sun converts the furious gamma rays of the core into a brilliant white light at the surface, a bit like allowing scalding steam to cool into warm water by the time it touches you. The photosphere is what we typically refer to as the sun's surface. Although being gaseous, the sun has no solid surface. It's the layer where the plasma becomes transparent enough for photons to finally escape into space. It's only a few hundred kilometers thick, razor thin compared to the sun's 700,000 kilometer radius. The photosphere's temperature is about 5,500 degrees in its upper layers, cooler than deeper inside, but still hot enough to glow bright. This is the light we see. When you safely project or filter an image of the sun, the features you observe, the mottled granulation, any sunspots, reside in the photosphere. As our photon escapes the sun and zips into the solar system, another ghostly traveler flies outward too, neutrinos. These nearly massless particles are produced in astronomical numbers by fusion reactions. Unlike photons, neutrinos interact so weakly with matter that they stream straight out of the sun's core and into space almost unhindered, reaching Earth in just over 8 minutes. Trillions pass through your body each second, unnoticed. They are like telegrams from the sun's core, confirming fusion is ongoing. We have built giant underground detectors to catch a handful of these elusive particles, and indeed, we have detected them, verifying that the sun's core is doing what our theory says. Neutrinos are essentially a direct line of sight to the sun's core, whereas photons only show us the surface. They've told us that the sun's output hasn't changed drastically in at least 100,000 years, and that our fusion calculations are correct within a few percent. So now, after an arduous journey, the energy birthed in the solar core has made it out. The sun's light is free, radiating into space in all directions. A minuscule fraction of it will intersect Earth, providing daylight and sustenance. The rest travels on, maybe to light up other planets, or just to disperse into the void. This continuous flow of energy from core to surface to space is the lifeblood of the sun. It is as if inside the sun, a story is written in energy, and that story travels for millennia to emerge as the light that then writes a chapter in the story of life on Earth. The many hues of sunlight. Step outside on a clear day and look at sunlight. To our eyes, it looks bright and roughly white or golden, depending on the time of day. But sunlight is not a single color or type of light. It is a symphony of many wavelengths of electromagnetic radiation, from high energy ultraviolet to visible colors to low energy infrared and beyond. The sun is often depicted as yellow in drawings, but in truth, the sun emits all colors of visible light blended together, which our eyes perceive as white. Our atmosphere can make the sun look yellow, orange, or red at times by scattering away the shorter wavelengths. But in space, the sun shines a near white. If we pass sunlight through a prism, it fans out into a rainbow, the solar spectrum. Every color from violet through red is present, fading seamlessly one into the next. This is the sun's visible fingerprint. Sprinkled in that rainbow, scientists have found dark lines, the Fraunhofer absorption lines, where elements in the sun's cooler outer layers absorb specific colors. By decoding those spectral lines, we learned which elements abound in the sun. Hydrogen and helium, overwhelmingly, with traces of almost every other element present in smaller amounts. In fact, those dark lines in the solar spectrum led to the discovery of helium in 1868. It was seen in the sun before it was found on Earth. The sun thus gave us helium, an element that remained hidden on Earth until later. But the sun's spectrum extends far beyond what our eyes can see. Ultraviolet radiation from the sun, invisible to us, is present in sunlight and carries more energy per photon than visible light. Most UV is fortunately blocked by Earth's ozone layer and atmosphere, but enough reaches the ground to give you a suntan or sunburn, a daily reminder that the sun outputs rays that can be both life-enabling and harmful. At even higher energies, the sun emits X-rays and even gamma rays, especially during solar flares, but those do not penetrate our atmosphere. On the other end, the sun emits plenty of infrared radiation, experienced by us as heat. Step into a patch of sunlight on a cool day and feel warmth on your skin. That's IR at work. Roughly half of the solar energy reaching Earth's surface is in the infrared. It's what warms the ground, oceans, and air. Plants reflect a lot of near-infrared, which is why they appear bright in infrared photography, but they eagerly absorb visible light for photosynthesis. The sun also emits radio waves, though relatively weakly in continuous spectrum. However, during solar flares or plasma oscillations, strong bursts of radio waves can occur, which we can pick up with antennas. Meanwhile, just below visible light is near ultraviolet, and just above violet is extreme ultraviolet. The sun emits those from its hotter regions, like the chromosphere and corona. Viewing the sun in different wavelengths reveals different stories. In ultraviolet, we see the chromosphere and lower corona as a dynamic network of loops and flashes. This is how satellites like SOHO and SDO image the sun's atmosphere and catch flares or eruptions. In visible light, we see the familiar yellow-white photosphere with sunspots, faculae, and granulation. In infrared, we can probe cooler features and sometimes see deeper into sunspot regions, and also observe the solar limb darkening effect clearly. In EUV and X-rays, we see the million-degree corona blazing from active regions, coronal loops, and coronal holes. In radio, we can study the sun's corona and even below the surface via radio emissions and detect burst events from flares. This broad spectrum underscores that the sun isn't just a static bulb of white light, but a multifaceted powerhouse. It also highlights how the sun affects Earth on many levels. UV shapes the upper atmosphere chemistry. Visible light fuels life and drives weather by heating Earth's surface unevenly. IR provides direct heat and is key to the greenhouse effect that keeps Earth warm. Interestingly, the sun's spectrum peaks in visible light, and not by accident. Our eyes evolved to be sensitive to the sun's peak output, and Earth's atmosphere has a window of transparency in the visible range. If the sun were a cooler red dwarf, peak output would be in infrared, and perhaps eyes on a planet there might evolve to see IR, or if hotter, eyes might see more UV or blue. And then there's invisible sunlight beyond the EM spectrum, neutrinos and the solar wind of charged particles. Both could be considered outputs of the sun in a broader sense. Solar wind shapes Earth's magnetosphere and is the cause of auroras, as we'll discuss. And neutrinos provide insight into the core. The solar constant is about 1,361 WD. This is what powers essentially all surface phenomena on Earth, from winds to ocean currents, to the water cycle and life itself. It's remarkably stable, varying only 0.1% over the 11th year cycle, and maybe up to 0.3% over centuries, if at all. The sun is more stable than many stars, which is fortunate for us because even a few percent variation could profoundly affect climate. That stability is one reason complex life could flourish on Earth. Our sun is a well-behaved star, not prone to large swings in luminosity. To sum up, the sun wears many colors. It emits a broad spectrum from radio waves to gamma rays. We see just a sliver, but modern instruments have expanded our vision. This multi-wavelength view has turned the sun from a blinding disk into a rich landscape of features. A calming white photosphere here, a violent UV flare there, a shining X-ray corona above. It reminds us that reality is often beyond human senses, and only by extending them do we fully appreciate the sun's grandeur. The next time you notice the golden light of late afternoon or enjoy the colors of a sunset, remember that this show is the result of the sun's rays interacting with our atmosphere. The reds and oranges of sunset happen because blue light has been scattered out, leaving the warm tones to travel through thick atmosphere to your eyes. It's a daily demonstration of the sun's spectrum and Earth's filtering, a touch of cosmic physics in an everyday experience. The sun's surface and atmosphere. The word surface is a bit misleading for the sun, since it has no solid crust. But when we say surface, we mean the photosphere, the visible disk from which light escapes. Just above the photosphere, the sun has an atmosphere of its own, layers of gas that are even more rarefied, where fascinating and sometimes puzzling things occur. Immediately above the photosphere lies the chromosphere, a region a few thousand kilometers thick. Normally, the chromosphere is hard to see because the photosphere's glare overwhelms it. It reveals itself in certain wavelengths or during solar eclipses as a thin pinkish rim around the sun. During a total eclipse, just as the sun is almost completely covered, observers often see a red flash or fringe. That's the chromosphere emitting light, notably the red glow of hydrogen gas. Early spectroscopists called it the flash spectrum. The chromosphere is a dynamic, fiery layer. It's populated by spicules, narrow, spike-like jets of plasma that shoot up from the photosphere into the chromosphere and last only minutes. Thousands of spicules are active at any time, giving the chromosphere a jagged, fur-like appearance in certain filters. The chromosphere is also threaded with filaments and plages. The temperature in the chromosphere actually rises with height, from about 4,500 K at the bottom to perhaps 20,000 K or more at the top. This is already a clue of some extra heating beyond simple radiative loss. Above the chromosphere, there's a thin transition region only a few hundred kilometers thick, where the temperature skyrockets from tens of thousands to nearly 1,000,000 Kelvin. Immediately above that is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is breathtaking. During a total solar eclipse, it's that pearly white crown we see encircling the black lunar silhouette. It's made of extremely hot, tenuous plasma. The corona is actually far less bright than the full moon. We can see it in eclipse only because the moon blocks the overwhelmingly brighter photosphere. One of the longest-standing puzzles in astrophysics is the coronal heating problem. Why is the sun's corona so hot when the sun's surface is relatively cool? Typically, if you move away from a heat source, temperature drops, like walking away from a fire. But above the photosphere, at first it drops. Then it leaps upward in the corona. It's as though you walked away from a campfire, and suddenly the air got scorching hot, far beyond the flames. Scientists suspect the sun's magnetic field is the culprit. The sun's surface and interior churn with electrically charged plasma, which twists magnetic field lines. These fields carry energy upward. There are a few ideas on how they deposit heat. Magnetic reconnection. Tangled magnetic field lines in the corona can snap and rejoin, releasing energy as heat. This could heat pockets of plasma to high temperatures. Waves. The turbulent motions of the photosphere might send upward Alfvén waves or other magneto-hydrodynamic waves that carry energy. When these waves reach the less dense corona, they could dissipate their energy as heat. Microjets or current sheets. Various small-scale dynamic phenomena in the lower corona might rapidly pump energy into coronal plasma. The Parker Solar Probe is actually gathering data relevant to this, diving into the corona to measure fields and particles directly. Early results have observed strange zigzag switchbacks in the magnetic field and bursts of plasma, providing clues. The solar orbiter has imaged omnipresent tiny flares on the solar surface, which might be part of the heating story. The corona is structured by the magnetic field. Above active sunspot regions, you get bright coronal loops in X-ray and EUV images, arches of plasma confined by magnetic lines, glowing at millions of degrees. In polar regions, or places with open field lines, you get coronal holes, which appear dark in X-ray EUV because they're cooler and less dense. These are sources of fast solar wind streams. The corona continuously expands into space, creating the solar wind. At some point, the plasma becomes so thin that particles escape the sun's gravity. That's the beginning of the wind. The boundary where the sun's atmosphere transitions to solar wind is not sharp. Essentially, the corona is the solar wind's birthplace. Now moving back inward, the chromosphere and corona aren't static shells. They are in constant flux. Solar flares often manifest as bright ribbons in the chromosphere and dazzling loops in the corona. When we monitor the sun in H-alpha, we primarily see chromospheric structures, filaments, plages, flares at their origin, and spicules at the limb. The photosphere, though cooler than the layers above, is where sunspots reside, and those spots have intense magnetic fields that shoot up into the corona, linking the layers. Think of sunspots as the visible feet of magnetic flux tubes that rise into the corona. Energy stored in those tubes can be released higher up. Our vantage from Earth's surface usually just shows us the bright photosphere. But with specialized solar telescopes and space observatories, we've managed to study these atmospheric layers intimately. The Solar Dynamics Observatory, for example, continuously images the sun in multiple wavelengths, giving us a 24/7 view of the chromosphere and corona dancing and flaring. It's inspiring that a total solar eclipse, one of nature's grand spectacles, was the key for humans discovering the chromosphere and corona well before the space age. During the eclipse of 1868, Jules Janssen and Norman Lockyer independently identified that mysterious yellow spectral line. During the eclipse of 1869 and others, observers noted green lines in the corona. Eclipses basically shouted to us, "There's more to the sun than meets the eye." Now we have artificial eclipses and advanced filters to monitor these layers routinely. We've directly imaged spicules, measured chromospheric magnetic fields, and observed the corona in X-ray movies over decades. Yet, even with all this, the solar atmosphere holds mysteries. We still debate exactly how the corona gets so hot. We don't fully understand the engine behind the 11th year cycle. We have difficulty predicting flares. We can see a region is ripe, but exactly when or how big a flare will go off is not yet predictable. We've realized the sun's atmosphere can even sing. It's filled with oscillations. The corona has waves and oscillatory phenomena that we can detect as periodic brightness changes. The sun is not quiet up there. It's ringing with acoustic vibrations, albeit far too thin to carry sound that we could hear with ears. Lastly, consider the scale. The corona seen during an eclipse extends several solar radii, but the influence of the sun's atmosphere actually reaches far beyond, effectively out to where the solar wind meets the interstellar medium. In that sense, the sun's atmosphere encompasses all the space where its particles and magnetic field extend. Earth orbits well within this realm, swimming in the solar atmosphere. We're effectively inside the sun's extended atmosphere all the time, in the solar wind's bubble. That's an astounding thought. We live inside the outer atmosphere of our star. So, summing up the sun's atmospheric layers: photosphere, 100 kilometers thick, 5,800 K. What we see as the surface: sunspots, granules, faculae live here. Chromosphere, few thousand kilometers thick, 10,000 K. Reddish glow in H alpha, home of spicules, filaments, magnetic network. Temperature rises with height. Transition region, very thin. Temperature shoots up to 1 million K. Corona, millions of kilometers, are 1,3 million K. Thin plasma shaped by magnetic fields, source of solar wind. Each layer is physically part of the sun, but conditions change so radically that we treat them as distinct zones. And through these layers, the sun's magnetic field is the scaffolding and the agitator. The sun's magnetic heartbeat. Peering at the sun over weeks and years, astronomers long ago noticed a curious pattern. The number of sunspots on the sun's face varies in a cycle, roughly every 11 years. At times, the sun's face is nearly clear, maybe a tiny spot, or none at all for days. This is solar minimum, the quiet phase. Years later, dozens of spots speckle the sun, some growing big enough to see without a telescope as tiny blemishes. That's solar maximum, the active phase. Then the activity wanes again. This rise and fall is the famous sunspot cycle. Sunspots themselves are regions where the sun's surface is cooler than the surroundings. A typical large sunspot might be around 4,000 K in its dark core, compared to 5,800 K in the bright photosphere. Spots often come in pairs or groups, with opposite magnetic polarity. Essentially, they are like north and south magnetic poles, poking through the photosphere. One spot will have magnetic field coming out, and the other nearby with field going in, connected by loops of magnetism above. Counting sunspots by eye and later by camera, people realized they follow this quasi-11th year oscillation. Around 1850, Rudolf Wolf pieced together historical records and came up with a sunspot number index that revealed this cycle. Today, we're in cycle 25. For perspective, cycle 24 peaked around 2014 with a modest number of spots. and then an extended quiet period occurred around 2018-2019. Now cycle 25 is ramping up, likely to peak around 2025 or 2026 with a moderate number of spots. The sunspot cycle is not perfectly regular. Some cycles are 9 years, some 14, but average have on 11. Also, the amplitude varies. Some cycles in the 20th century were very strong, while some in the 19th were weaker. The 17th century Maunder minimum was an extreme case. Very few sunspots were recorded from about 1645 to 1715, a period that coincided with cooler climate in Europe. There's evidence from carbon in tree rings that other grand minima occurred in the past. So the sun's cycle itself modulates on longer timescales. What causes the cycle? The root is the sun's magnetic dynamo, the mechanism by which the sun generates its magnetic field. The sun rotates and has huge convective motions in its outer layers, plus likely a shear layer at the base of the convection zone. The interplay of these motions stretches and twists magnetic field lines inside the sun. Roughly every 11 years, the field gets so twisted that it resets. The sun's global magnetic polarity flips. It then takes another 11 years to flip back, so the full magnetic cycle is 22 years. Sunspots are a direct manifestation of this magnetic cycle. Early in a cycle, the first spots of the new cycle appear at mid-high solar latitudes. They often come in with reversed polarity compared to last cycle's spots. As the cycle progresses toward maximum, spots appear in greater numbers and at lower latitudes. Near the peak, you might see spots even 5,010 degrees from the equator. After maximum, as the cycle decays, spots get scarcer and cluster near the equator. Then it resets. No spots at the equator, and new spots of opposite polarity start popping up back at high latitudes for the next cycle. If you plot latitude of spots over time, you get the butterfly diagram. 2 wings per cycle descending toward the equator. Sunspots come and go over days to weeks. They often emerge, grow, break apart, or explode. They often appear in active regions, an area with complex magnetic structure, including multiple spots, faculae, plages, etc. Those are the ones likely to produce flares and CMEs. During solar maximum, the whole sun is magnetically disturbed. The corona is full of bright active region loops. There are more flares, and the sun's overall UV and X-ray output is higher. At solar minimum, the corona is simpler, with big coronal holes at the poles and few bright loops, and the sun's X-ray brightness can drop to nearly nothing. It's important to note the cycle isn't perfectly uniform. Sometimes big sunspots or storms happen in the decline phase, etc. But overall, more sunspots means more potential for solar storms, and vice versa. Now, why should we care about the sunspot cycle? It's not just academic. It drives the space weather environment around Earth. During high sunspot years, we get more frequent solar flares and CMEs, meaning more auroras and geomagnetic storms on Earth, as well as more radiation hazards for satellites' astronauts. During low years, space weather is quieter, but interestingly, cosmic ray flux at Earth increases. Also, the outer atmosphere of Earth cools and contracts during solar min due to less EUV heating, which can affect satellite orbits. So even earthly systems respond to the cycle. For example, the upper atmosphere density difference between solar max and min is significant for orbiting objects. Also, one's view of the polar aurora oval expands in solar max and shrinks in solar min. Radio communications on Earth are affected by the cycle too. HF radio propagation tends to be better around solar max because the ionosphere is more ionized, while during solar mine, certain frequencies propagate poorly. So the sun's 11th year heartbeat sends ripples through our technology and environment. On the sun itself, the cycle orchestrates phenomena. The polarity of sunspots flips each cycle. The number of prominences, flares, sunspots, faculae all follow the cycle. Even the solar poles reverse their magnetic field at each maximum. Yes, the sun's north and south magnetic poles flip around the time of sunspot peak. That's when the global field is weakest and messy, then a new polarity builds and settles by the next min. To get a little deeper, when the sun approaches minimum, often the last spots of the old cycle linger near equator. But already by then, new spots from the next cycle might have appeared at high latitudes. So cycles actually overlap slightly. We identify cycles by when the old spots mostly vanish and new ones dominate. Magnetic oddities occur too. Occasionally, there are short breaks in cycles or irregularities. We don't fully understand the sun's long-term magnetic modulation. It might have 50-year, 100-year variations. Some predict another grand minimum could occur, but that's uncertain. The cycle also has asymmetries. Typically, one hemisphere of the sun leads or dominates in a given cycle. For instance, the north might erupt earlier and have more spots one cycle, and the south might dominate the next, etc. This is an active area of research, trying to see patterns in these differences. Now, what exactly are sunspots in physical terms? They are concentrations of strong magnetic field on the order of 0.1 to 0.4 Tesla. For comparison, Earth's surface magnetic field is about 0.0005 Tesla, so sunspot fields are thousands of times stronger than Earth's field. These fields suppress convection locally, so less hot material rises, and the area cools relative to surroundings, hence looks dark. A sunspot often has a dark core and a surrounding mottled, lighter grey area with filamentary structure. Those penumbral filaments are somewhat convective flows channeled by the field. Sunspots can be as small as a few hundred kilometers or as large as 50,000 kilometers across. Galileo's drawings show some large ones visible to the projection technique he used. The biggest tend to appear around solar max. Sunspots often appear in pairs, roughly east, west of each other. One will be magnetically north, the other south. In the next hemisphere, the polarity orientation is reversed. In the next cycle, all that flips. So, summing up, the sun has a magnetic heartbeat of 11 years. It's like a slow pulse, where every beat inverts the field. With each beat, the sun goes from calm to active to calm again. At the peak, it shows its magnetic muscles via sunspots and flares. During the lull, it's magnetically catching its breath, reorganizing for the next wave. We have kept count of these beats for centuries now, and while each has its own character, the persistence of the cycle is a remarkable feature of our star. Many stars show magnetic cycles too, but the sun's is the one we have in most detail. Understanding the cycle isn't just for curiosity. It helps anticipate periods of greater solar storm risk, plan satellite launches. It also feeds into climate discussions. Tiny solar output variations might have slight influence on climate, though current climate change is dominated by anthropogenic effects. This magnetic heartbeat will continue for a few billion more years, but as the sun evolves into a giant later, it will likely become more erratic or different. Red giants can have magnetic fields, but often not cycles like the sun's. That's far ahead though. For now, we are mid-cycle in cycle 25. In a few years, we'll likely see a lively sun peppered with spots and laced with flares, a good time for aurora watchers. Then it will calm down again. The dance goes on. Storms on the sun. The sun's magnetic cycle not only brings dark spots but also violent outbursts. When magnetic energy that's been stored in twisted field lines suddenly releases, the sun experiences storms, primarily solar flares and coronal mass ejections. These are the most dramatic manifestations of a star's magnetic wrath, and they can have direct consequences many millions of kilometers away on Earth. Solar flares are essentially gigantic explosions in the sun's atmosphere. In minutes, a localized region on the sun can release as much energy as billions of nuclear bombs. A flare brightens across the spectrum. Intense X-rays and extreme UV pour out. Visible light can even increase in what's called a white light flare, and radio waves and gamma rays might be emitted too. Flares are classified by their X-ray brightness as observed by Earth orbiting satellites. The classes are A, B, C, M, X, each a step up by factor of 10. A is very small, B small, C moderate, M medium, large, X large. Within each letter class, they use a numeric scale from 1 to 9. For example, an X2 flare is twice as strong as X1 and 4 times as strong as an M5. The biggest flares recorded by modern instruments were about X28 in 2003. The Carrington event flare in 1859 is inferred to be perhaps X-class in the 30s, though direct measurement didn't exist. What triggers a flare? Magnetic reconnection is the key. Imagine magnetic field lines arching out of a sunspot pair like loops. If these lines become stressed and tangled enough, they can snap and reconnect in a lower energy configuration, like a rubber band breaking. When that happens, all the energy that was stored in the twist of the magnetic field is suddenly released as heat, light, motion, and particle acceleration. The plasma in that region gets superheated. Electrons are hurled to near light speed, spiraling along field lines, and protons and heavier ions are likewise accelerated. In images, a flare often appears as a bright flash or set of ribbons in H, alpha, or UV on the solar disk. Then you see post-flare loops, graceful glowing arcs in the aftermath as the hot plasma cools and settles in magnetic loops. Flares can happen without a CME, especially smaller ones, but big flares often coincide with a CME. Coronal mass ejections are colossal eruptions of solar plasma and magnetic field into space. Think of it as the sun belching out a piece of its atmosphere. A CME typically involves a twisted flux rope of magnetic field that suddenly ejects, carrying with it billions of tons of coronal gas. CMEs travel at speeds from a few hundred km/s to up to 200 to 500 pounds/km/s for really fast ones. At Earth's distance, that's about 1 to 3 days of travel. We often see CMEs with coronagraphs, a halo or a bright loop structure expanding away from the sun. If a CME is coming toward Earth, we might see a halo CME. Many strong flares have an associated CME, but not all. And you can have a CME without a big flare if a region's field slowly destabilizes and erupts without a sudden flash. Now, when these storms occur, what do they do to Earth? This brings us to space weather effects. Electromagnetic radiation from a flare, X-rays, and UV arrive in 8 minutes at Earth. They ionize the upper atmosphere. This can cause radio blackouts for HF communications. GPS signals can be degraded. Essentially, a strong X-class flare can temporarily deafen our ionospheric radio wave propagation on the sunlit side. This is called an R event in NOAA space weather scales. The effect typically lasts an hour or a few hours as the ionosphere gradually recombines. Solar energetic particles. Some flares accelerate particles, mainly protons, to near relativistic speeds. These proton storms can arrive in tens of minutes to hours after the flare. These particles pose a radiation hazard. They are deflected by Earth's magnetic field for the most part, but some get funneled toward the poles, causing a shower of ionization in the atmosphere. On high-altitude polar flights, this can increase radiation dose to passengers and crews. For astronauts, especially outside the ISS, it can be dangerous without shelter. SEPs can also physically damage satellites, penetrating electronics, causing bit flips, charging surfaces leading to discharges, degrading solar panels and materials. NOAA calls these S events, scaled S1 to S5. An S3 or above can prompt airlines to reroute polar flights to lower latitudes. During one event in 2012, some airlines did this as precaution. Coronal mass ejection impact. When the CME cloud arrives a day or two later, it's the geomagnetic storm time. The CME plasma carries embedded magnetic fields. If the magnetic field in the CME is oriented southward, when it hits Earth, it couples strongly with Earth's northward field. This injects energy and plasma into our magnetosphere and triggers a geomagnetic storm. A geomagnetic storm is essentially a global disturbance in Earth's magnetic field. It causes beautiful auroras. It also can induce electric currents in long conductors on the ground, notably power lines and pipelines. In extreme cases, these currents can overload transformers in power grids, causing blackouts. The classic example, the Carrington event of 1859, caused telegraph lines to spark and even caught telegraph paper on fire. Operators got shocked. Some telegraph systems continued to operate on auroral currents alone after disconnecting batteries. If such an event struck today, studies suggest it could severely damage electric grids and satellites globally, potentially causing trillions in damages. A more recent case, March 1989, a strong CME hit Earth and caused a geomagnetic storm that collapsed Quebec's power grid within seconds. Millions lost power for hours, and some transformers were permanently damaged. In the same storm, auroras were seen as far south as Texas and Florida. Another event in Halloween 2003 caused less grid damage, but did affect satellites and caused a geomagnetic storm that disrupted parts of Sweden's grid and affected airline comms. And in 2005, a lesser-known storm still caused GPS outages for hours due to ionospheric disturbances. So, geomagnetic storms matter. They are rated by NOAA as G1 to G5 based on how much Earth's magnetic field deviates. G5 events are rare. The last truly extreme one was 2003's Halloween storm. During storms, auroras can be seen much farther from the poles than usual. People in mid-latitudes who rarely see them might get a treat. Red auroras overhead, green curtains on the horizon. It's often a surprise and delight. Historically, low-latitude auroras freaked people out. Besides auroras and power issues, geomagnetic storms can disturb navigation and create extra drag on low-orbit satellites by heating the upper atmosphere. We can often get some warning. Satellites like ACE or DSCO VR at L1 measure the solar wind about 1 million miles upstream, giving us 30,000 60 minutes notice of the CME's magnetic orientation and velocity before it hits Earth. That helps alert power grid operators to prepare. Spacecraft can be put in safe mode to avoid damage from high-energy particles. Astronauts can take cover in shielded parts of the ISS. Airlines can reroute flights. These mitigations rely on us detecting the sun's storms soon after they start and monitoring the in situ wind. Now, not every solar storm hits Earth. The sun is blasting things out all the time in various directions. Earth, a small target, intersects only some. Sometimes we see a huge flare in CME, but it goes off to the side. Other times, a seemingly modest flare may send a CME squarely toward us and catch us head-on. Space weather forecasters analyze coronagraph images and measure CME speeds to predict arrival times. While the largest events are rare, even moderate storms can be disruptive. For example, the Halloween storms of 2003 caused 2 large geomagnetic storms, damaged or disrupted satellites, rerouted flights, and gave spectacular auroras. That was with sunspot cycle 23 near end. It's interesting that sometimes big flares don't produce proportionally big geostorms. It depends on the CME magnetic alignment. In 2012, a monster CME shot out, but missed Earth. In 2015, a strong CME's field wasn't southward, so it produced a milder storm than expected. Beyond Earth, solar storms can affect other planets too, of course. Mars, lacking a strong global magnetosphere, gets walloped more directly. Its atmosphere gets eroded gradually by many CME hits. Jupiter's magnetic field responds with its own auroras and disturbances. Solar flares also have interesting effects. They can cause cosmic ray intensity to drop because the expanded solar wind and magnetic flux after a CME sweeps away some cosmic rays for a few days. One might wonder, could a solar flare or CME directly harm life on Earth's surface? Thanks to our atmosphere and magnetosphere, not really. Even the worst case solar particle storm might up the radiation slightly at ground level, but not enough to be lethal or cause immediate issues for humans. The risk is more to technology. Perhaps if a truly gigantic flare happened, you might see minor radiation effects at aircraft altitudes. But life has survived countless solar storms over billions of years. The sun's variability is modest enough that it hasn't sterilized Earth. For astronauts on Mars or future moon bases, though, these storms are a significant hazard outside of Earth's magnetic cradle. A big solar particle event can deliver a potentially lethal dose of radiation if astronauts are caught unprotected. This happened, fortunately in timing, in August 1972, a huge solar proton storm between Apollo 16 and 17 missions. Had astronauts been en route to the moon then, they could have been in serious danger. So space agencies plan to have shelters and storm forecasts for deep space missions. The interplay of flares, CMEs, and cosmic rays also extends to potentially affecting Earth's clouds or climate slightly. There's an interesting possible link. During strong solar activity, cosmic rays are reduced, and some scientists speculated that fewer cosmic rays mean fewer cloud seeds. Thus, in times of high solar activity, maybe slightly less cloud cover and a tad more warming, and vice versa. This theory is still debated. Evidence isn't very strong that cosmic ray changes make large climate differences, but it's an intriguing idea connecting solar magnetism to weather. In summary, solar storms are the climax of the sun's magnetic drama. They turn the sun from a steady light into an occasional threat. For much of history, humans noticed their side effects only as awe-inspiring auroras or disrupted telegraphs. Today, in our interconnected, electrified world, we watch the sun closely because a big storm could mean days without power or lost satellites. It's fascinating and a little unsettling that our mild-looking sun can flex such power across space. At the same time, these storms have likely been occurring for eons, and life persisted. They may have even helped Earth's atmosphere over geological time by providing energy for chemical reactions or by injecting atmospheric nitrogen oxides. On some level, they remind us the sun is not a static lamp, but a star, and all stars have tempests. The sun and Earth, a delicate balance. Despite the sun's occasional violence, it is indisputable that without it, Earth would be lifeless. The sun sits at just the right distance to make Earth a comfortable habitat. The sun sustains life in every way. It provides virtually all the energy that drives Earth's climate and ecosystems. If the sun's light stopped for even a week, Earth would plunge into deep freeze and most life would perish shortly after. Let's walk through the many threads of connection between the sun and life. Photosynthesis, the basis of the food chain. Plants, algae, and cyanobacteria capture sunlight and use its energy to turn carbon dioxide and water into sugars and oxygen. This process, which has been ongoing for 2-3 billion years, created the oxygen-rich atmosphere we breathe and feeds almost all organisms directly or indirectly. When you eat a piece of bread or fruit, you're consuming stored sunshine, the plant that made it packaged solar energy into a chemical form. Even fossil fuels are ancient sunlight. Coal, oil, and gas are the remains of plants and plankton from hundreds of millions of years ago who used sunlight to grow. Burning those fuels releases that solar energy that was stored long ago. Thus, quite literally, all life is sunlight, slowed down and transformed. A poetic but true statement. We are all made of sunshine. The calories you burn with each breath were gathered by a plant from the sun. If the sun had not shone, Earth might have some chemical energy life at deep-sea vents, but likely nothing like the thriving biosphere we know. Climate and weather. The sun's energy drives the circulation of our atmosphere and oceans. The equator gets more direct sunlight than the poles, creating temperature gradients. Warm air rises at the equator, flows toward poles, cools and sinks, setting up convection cells that produce prevailing winds and weather patterns. The rotation of Earth and the distribution of continents complicate it, but fundamentally, wind exists because the sun heats some parts of Earth more than others. The water cycle, evaporation, cloud formation, rain, rivers flowing, is powered by solar heating of the oceans and land. No sunlight, no evaporation, no rain. The sun lifts water vapor up, which then condenses and falls as precipitation, enabling terrestrial life and shaping landscapes. Day-night rhythms. The daily cycle of light and dark has imprinted itself on life's behavior and physiology. Almost all organisms have circadian rhythms, internal clocks attuned to the 24-hour cycle of light and darkness. Humans get sleepy after sunset because our pineal gland produces melatonin in the dark. Sunlight each morning resets our circadian clock, syncing our sleep-wake with the outside world. Plants orient their leaves or open their flowers with the sun. Animals might be nocturnal or diurnal, depending on how they've adapted to the presence or absence of light. Before artificial light, human activity was largely diurnal. We did things in daylight and rested at night. Even now, many of us find bright light at night disruptive and a sunny day energizing, which is a deep evolutionary wiring. Seasons. Earth's axial tilt means the sun's angle changes over the year, giving seasons. In winter, less sun and lower angle leads to cold. In summer, more sun and higher angle leads to warmth. Life evolved strategies to cope. Deciduous trees shed leaves in temperate winter to avoid frost damage when sunlight is too weak to support them. Animals hibernate or migrate to follow the sun's warmth. Crop planting cycles align with seasons. Civilizations developed calendars to predict solstices and equinoxes. These allowed planning of agriculture and festivals. Many cultures celebrated the winter solstice as a time of rebirth and hope. Indeed, our modern holidays like Christmas align with ancient solstice festivals like Saturnalia or Yule, essentially celebrations of the sun's return. Psychological impact. The sun and its light have a direct effect on mood. Winter blues, or seasonal affective disorder, is a depression that hits some people in dark winter months. It's linked to lower sunlight causing changes in brain chemistry. Treatment often includes light therapy, essentially giving people artificial sunlight to cheer up their brains. We use sunny metaphors for happiness and dark for sadness, which shows a universal intuition. Sunlight correlates with positive feelings, darkness with gloom. Physical health. Sunlight triggers the production of vitamin D in human skin, which is essential for bone health and immune function. Historically, societies in low sunlight regions had diets to compensate to avoid rickets. Conversely, too much sun can cause skin damage or cancer. So there's a balance organisms must strike between harnessing the sun and being harmed by it. Sunlight also helps regulate various bodily functions, from sleep cycles to potentially blood pressure. Moderate sun exposure tends to correlate with certain health benefits, whereas none or too much have downsides. Oceans and currents. Sun warms equatorial waters more than polar. That drives global ocean currents. These currents shape climates. The sun's uneven heating of Earth thus orchestrates even these deep ocean patterns. Extreme dependence. Virtually nothing on Earth is untouched by the sun. Even cave ecosystems that never see sunlight ultimately rely on energy that originally came from the surface. Only some rare ecosystems like deep sea vents might circumvent the sun by using Earth's internal heat and chemistry as an energy source. interestingly giving us clues how life could exist on sunless worlds like Europa's ocean or under Titan's crust. But those are exceptions. The bounty and complexity of life we know is thanks to the sun's abundant energy pouring down. Protective shields. The sun's magnetic field, via the solar wind, also helps shield the inner solar system from some cosmic rays. Earth's magnetic field, in turn, shields us from much of the solar wind. It's like layers of defense. Earth's magnetosphere and atmosphere protect life from most harmful space radiation. Without the sun's stable output and Earth's shielding, life on land would be very different or impossible. The far future. The sun won't always be so kind. In about 1 billion years, as it brightens, Earth might get too hot for comfort. That would be a slow, moving disaster, though. Later, in 5 billion years, the sun will expand to a red giant and likely end the Earth as we know it. But by then, maybe our descendants will have migrated elsewhere or adapted in ways we can't imagine. It's worth noting that while the sun's output is currently steady, even small changes have been linked to climate shifts historically. The sun might have influenced Earth's climate slightly over centuries. Now, human factors are overpowering such subtle solar changes. Beyond physics and biology, the sun influenced culture and religion profoundly, as covered earlier. Rulers aligned themselves with the sun. Ancient Egyptians had a whole theology around the sun's cycle. The Japanese emperor was believed to descend from Amaterasu, the sun goddess. The sun was a universal symbol for life, energy, and rebirth. Even today, in language, we have vestiges. Sunday, literally Sun's Day. Many national flags have suns. We celebrate things like the summer solstice in festivals. Science gave us a more factual, less mystical sun, but we still greet a sunny morning with a certain joy. So the balance is, the sun gives us life and sometimes threatens it, but mostly sustains. Earth has been lucky to have a star of just the right mass. More massive stars burn out too fast. Less massive ones might be too fickle, or have planets too close and tidally locked. Our sun is indeed a fairly ordinary star, but for us, it is extraordinary, the one and only source of light and life. Astronauts orbiting Earth often remark on the stunning view of the sun cresting our blue atmosphere, sometimes calling it a fragile layer protecting us. If you watch an orbital sunrise from the ISS, you see a bright point intensify, and then a blazing star burst over the horizon with a jewel, like thin blue line beneath. A visceral reminder of how dependent we are on that light, and on that tenuous air to moderate it for us. We live in the sun's extended atmosphere. We eat its light. We feel its warmth. We fear its storms, and we bask in its glory. That relationship has defined Earth's story from the very beginning. Life's emergence, evolution, and ultimately maybe life's end here when the sun changes state. To put it succinctly, if Earth is our mother, then the sun is our father, providing the energy of life. Both are needed, and indeed many cultures personified them that way. Even going beyond Earth, when we search for habitable exoplanets, we're basically hunting for other Earths around other suns. The conditions that make Earth habitable revolve around having a star like the sun at the right distance, plus Earth's own attributes. We basically look for similar star-planet arrangements because we recognize how fundamental the star's role is. In closing this segment, every warm breeze, every raindrop, every green leaf, every breath of oxygen, every shimmering aurora, all trace back to our sun. It's truly the heart of our existence. The Earth-Sun connection is intimate and profound. Understanding that scientifically doesn't diminish its wonder, it enhances it, as we see even more clearly how finely tuned and interwoven the system is. The sun's living past and future. We've journeyed through the sun's present workings, but the sun's story has a timeline, a biography from birth to death, with Earth riding along for part of the way. Let's step back to understand where our sun came from and where it is going, and how that shapes the broader narrative of stars and life. Birth recap. Our sun ignited about 4.6 billion years ago, likely in a cluster with siblings. We see evidence of a nearby supernova explosion around the time of the sun's birth. Certain isotopes in meteorites suggest that a supernova shockwave might have triggered the collapse of the molecular cloud that formed our solar system. So perhaps a massive star's death helped spark the sun's birth. In that cloud, not just the sun, but other stars would have formed. We find some solar sibling candidates by chemistry and motion in the galaxy, but over 4+ billion years, the cluster dispersed. As a young star, the sun was likely more active. Young suns spin faster and have more flares, strong winds. There's evidence Earth's early atmosphere experienced intense solar winds and flares. But fortunately, by the time life arose, the sun had probably calmed to a more stable state, though still a bit dimmer than today. The faint young sun paradox. Astrophysical models say the sun was 30%. The response is very long and presumably covers all points requested.